All right. Hello, welcome to the last day of our HPC workshop. Hmm, Today, thank you. Today, we will do more of the parallel programming part. So we start with writing a vectorized program, then writing an OpenMP threaded program using shared memory, and finally uh, MPI, that's like message passing for distributed memory system. And then you can try to combine all those approaches together on some simple example. So I will start with some theory or explanation um, about what we're going to do today. So we will implement the parallel algorithms, some of the basic ideas we talked about in previous sessions. So if you're implementing a parallel algorithm, usually the first thing to do is actually to implement a serial algorithm and then continue with parallelizing it. The reason for that is that it's of course much easier to write serial programs than parallel programs. And if you have a serial prototype, at least in some higher level language, for example, like, I don't know, Python or MATLAB or something like that, then you always have a way to compare the results of your parallel algorithm to that serial algorithm. And you can somehow divide those ideas or methods of parallelization into like lower level and higher level. On the low level, you need to think about vectorization and with vectorization and about your data types, about the way your data is laid out in memory, mm, proper utilization of cache, because you remember uh, different different memory types have very disparate latencies. So you want to have your data as close to the CPU as possible. And on the higher level, you think about the algorithm itself, that is this realization of the parallel patterns we talked about yesterday. So some of those patterns, like map, that's something you can directly, and that's basically the only thing we will be doing today. That's something you can directly apply to your program just by partitioning your data and then having your individual processing units operate on that data. But of course, there are some um, uh, in case you have some data dependencies, this cannot in most cases, or in many cases, this cannot be directly employed as is. So then you need to either find some specific algorithm, a parallel pattern that fits, or in the worst case, you just out of luck and you have a piece of code that has to be run in serial fashion. And somewhat in the middle, but like I would still say high level, because uh, it affects the structure of your program, is this realization of those parallel patterns, either by thread dispatching with on a shared memory system, or by sending messages on MPI system. CUDA is basically kind of like something between low and high level because it's something between threading and vectorization, let's say. I will just briefly mention it at the end. So, vectorization. Remember, vectorization is when you perform one operation on multiple operands at the same time. So that's why you call it SIMD, single instruction, multiple data architecture. So you have in the hardware, it's realized by the CPU having some SIMD instructions. There are those instructions which that's what performs the operations, and the registers, those are pieces of memory directly on the CPU, and the instruction circuits can directly access those registers. If something is not in the register, in order for the instruction to operate on that thing, it needs to get to the register first. Intel architectures are still the most common you will encounter. But yes, as we talked about it on the first day, of course, you also have those ARM architectures. Evolving RISC-V architecture is a promising one for future, and there are also those power chips and similar, but still the vast majority of computing clusters and almost all personal computers, be it laptops or desktops, are based on this Intel architecture. So nowadays that's being produced by Intel and AMD. Intel first introduced vectorized instructions in 1997 with which is this multimedia extensions instruction set with 80-bit registers only for integers. It was, as the name suggests, made for accelerating algorithms in image manipulation, video compression, and I don't know if sound was there as well, maybe, but like images and video specifically, that was the big hit in '97. Then in '99 they introduced this. I'm not exactly sure if SSE was introduced by Intel or by AMD. I think one of those sets was first implemented by AMD, and then Intel got it in their chips as well. So SSE stands for streaming streaming extension.
SIMD extension.
Oh, streaming streaming SIMD extension. And in '99, it introduced those 128-bit floating point registers, and that's something that's already interesting for scientific codes. So a single precision floating point number is what 4 bytes, 32 bits. So this register can hold 4 single precision floats, and 2 years later, SSE2 was introduced, which also allowed to hold double precision numbers in the register. So the size of the register stay the same, but you have another type of register that can, instead of holding 4 floats, it can hold two doubles. And then for a couple of years, they were like different versions of SSE were adding new types of instructions. but everything still operated in those on those 128-bit registers until 2008, where AVX was introduced. And AVX, I completely forgot what that means. Advanced Vector Extensions. So advanced vector extensions increase the length of the register to 256 bits. So it can hold 4 double precision numbers or eight single precision floats, and that's already like if you're doing calculations in double precision, then maybe like just like using 2 is not that interesting. Increasing that to 4 is interesting for sure. And then yes, of course, everything gets longer, bigger. So AVX 512 was introduced in 2016, again doubling the size of the register and the instructions. Originally, this was only available on those Intel Xeon Phi like computing accelerators, so something like a GPU, but with a more sophisticated processor. Basically, those Xeon Phi were supported the full instruction set of the regular x86 architecture with this AVX 5012 instructions added, but it had many cores, something like 80 cores or something. But it, for example, didn't have much of a branch prediction, and so it was a simple. In certain ways, the chip was of a more simple design than the CPUs, but at the same time, it was a more complex design in terms of instructions than the GPUs. And back then, the biggest GPUs I think had about like 1,000 stream processors. Nowadays, it's like several thousands, like 5,000 or something. And this and the CPUs, I don't know if they had like 12 core CPUs for servers, something like that. But like so this compute accelerator from Intel was like somewhere the middle ground between a CPU and a GPU, but then it kind of fell off with the advent of better programmer tools, because it was easier to program for it than programming for CUDA, because you could use like the same ideas, same algorithms, same even the same compilers, but then NVIDIA pushed like some better tools for programming for CUDA, so this Intel idea kind of became irrelevant. But the newest, the last, I don't know, 2 or 3 generations of desktop and server CPUs also support those AVX 5012-bit registers, but with some gotchas. Like, for example, if you use them, the CPU will automatically switch to this like clock down to the baseline clock amount, so you cannot use this like turbo boost feature of the Intel processors. It also on some architectures, I think there was like some issue with like register sharing or something like that. So in real programs, actually going from AVX to AVX 512 quite often doesn't increase the performance at all, and it's still I mean in the latest server processors, this is not that big of an issue. But if you try to Google for more information, you will even find Intel forums where official Intel hardware developers will tell you that they're unable to, like, if you ask them, so is this CPU like okay, or like will it work on the CPU? They will tell you, oh, we don't know. It's like a very difficult question. So it's but I mean, at some point, very likely the circuits will get optimized, maybe in some next generation of CPUs, that this will not be an issue, and then the scientific world will very likely switch to AVX 512. But nowadays, still AVX2 is the most relevant one, and unless you're doing some really specialized calculations and have them tested. So how do we create a vectorized program, or how do we implement that and how it works? So typical example, I have a vector field made of n 3D vectors, and like naturally, so if I have a vector register, my first idea would be to this is the vector type 128 bits, so this is an SST type which holds 4 floats. So I can store those 3 floats into this 4 float type. Just ignore the last element, load my numbers into the vector register, and then perform this vector as a C equals A plus B as a vector operation in a single instruction. So I create this vector holding the vector. I have those like 3 vectors, and I call this special function. Those are available in C and C++. They're called intrinsic functions, and those intrinsics are basically almost one-to-one mapped to the actual instructions, but yeah, they behave like C or C++ functions. So this is a function call for addition in C++, and maybe in C even. I'm not exactly sure, but it's also possible to just use the operator plus, and it will correctly call the instruction you want it. But like explicitly, this is what you can write. And it's simple, it makes sense, it's kind of natural because I have a vector, mathematical vector, so I put it into the hardware vector. But it's not a scalable approach because even in this simple but very common case of 3D vectors, if I did it like this, I'm wasting that float, that element here, because I'm only utilizing 3, and if I use like even AVX architecture, a longer one which holds 8 floats, then doing this way, there would be like 5 floats, five elements skip.
How hard is it to do like bit hacking in this case when you know that you have 3-dimensional vector, but you want to do something extra, and you start doing something with the fourth one, also like dragging it all together, or this set of instructions is very limited. This intrinsic function. I mean,
There's a lot of them.
You can do all sorts of like, yeah, it will be like
okay, so
to do with it, but you can do all these abstractions where you make your own structures and then like do complicated things with them, which is very like hard coded for you specifically.
Well, yes, but in the end, most of the algorithms will boil down to some algebraic operations, and for that you have like all those instructions that you know. There are also some specialized vector instructions for like some common I don't know if they are like trigonometric functions. I don't remember, but I think they are, and like reciprocal function and like those which are commonly used. There's a on the AVX 512. There's this fused multiply add operation, where in the same instruction you multiplying by a number and adding a number, which is which can especially speed up matrix multiplication, because that's exactly what you're doing in every step of matrix multiplication. So that's something that was kind of invented or put there because of the scientific simulations where matrix multiplication is like super common.
Yeah, and there are four flaws, but in scientific calculations you could have doubles.
Oh, yeah. So that you, yes, in other instructions. So here you can either put four floats or two doubles, and in this AVX2 that can hold four doubles. Yeah. And yes, I mean, in a lot of scientific simulations you do.
Much less data.
Yes, but then you when you go to AVX2, then it's the same situation again. You're only using 3/4 of the available power. Well, one thing about doubles and floats in scientific simulations with vector instructions and especially with GPUs, like working with floats is much faster than working with doubles. So in some situations, if you are able to reconstruct your algorithm so that it can allow for this lower precision, it might be well worth it, because all the operations on float will be like much faster than the operations on doubles.
Now that some start from one double, two floats, and then process like with floats. Is it guarantee some speed up or not? I'm not sure.
Oh, in single threaded code, probably not. But in vectorized code and in especially in GPU code,
Yeah.
the result is can be quite huge. So like it can literally be like double the double the speed. So sometimes it's worth it. Like for some specific algorithms, there are tricks to do that, but of course you always need to you need to know whether you need that extended precision, and if you do need it, then yes, then you just do calculation in doubles.
But it's not that rare, as far as I know. If I remember correctly, even in plasma physics calculation,
Yes,
it's often the case that you need to run the algorithm for a long time and it starts diverging. So that it doesn't diverge, you need extra precision. Well, no? Not for any
there's
calculation,
many. I mean, there's many other issues with computer precision. I mean, we can do another workshop. Usually, I taught this at the university at the basics of numerical methods. But if you're interested in details, you can look for a paper which is called "What Every Programmer Should Know About Floating Point Numbers." Should know about floating point numbers, and I don't know. I even don't know who wrote it, but like, read it. It's interesting. It's an interesting read, and explains a lot of the issues that arise with floating point numbers, and a lot of unexpected features of floating point numbers, which make them like not really behave as the natural numbers.
Can you send it just to the group chat?
Oh, about floating point arithmetic. Yeah. Okay. So, here is F. Why do computers use such a stupid system, etc. It's a great paper and like very illuminating. So I definitely recommend reading this, and it's not long. Yeah, it has some just like I don't know, about 15 pages. You can read it pretty quickly, unlike the other, which I will show you in a couple of minutes probably. So, um, yeah. So, like I said, those instructions are called intrinsics, and they are more or less directly translated to appropriate vector instructions by the compiler. You can find the list of the instructions again by Googling. Usually, you will come to some Intel white paper listing all the instructions available for your processor. You can also use this if you're working on a cluster or like you're on Linux. Then if you check this proc CPU info, if you remember from the first lesson, you will also find a line that lists all the features of the processor, and a lot of those features are different versions of those SSE and AVX extensions. So this is what they look like for SSE and AVX. MM is for the SSE 128-bit number. MM256 are the AVX instructions. Then of course you have like MM 512 for the AVX 512 instructions, and here the registers are like look always the same, and the function itself has the specification whether it's working on single precision floats or on doubles. And most modern compilers also understands constructs like A plus B instead of this at PS. Um, I don't know if it's in C, if it's true in C as well. It's definitely true in C++. And also, modern compilers will auto-vectorize your inner loops if this is not prevented by loop dependencies or some insuitable data type that is being used in the loop. And the compilers are pretty smart about it. And when I was preparing the lectures, I also found out that it can be very difficult to actually force the compiler not to do the auto-vectorization on at least some level, because like all compilers now correctly assume that if you're on a 64-bit architecture, you have like at least this SSE 4.2 available, and it's like their baseline assumption. And
4.2 is optional. SSE2 is.
Okay, maybe SSE2, yeah. But like there's some baseline on those Intel 64-bit architectures, which just like and it's very difficult to tell the compiler not to use it at all if you really want to show how it behaves. So yeah. A lot of time the compiler on like with you when you select the correct optimization level, he will do this for you if your code is at least somehow ready for it. And I said that this natural, let's say, idea of mapping a vector on a vector is not optimal, especially on those long architectures. So what we should do is that instead is so-called horizontal vectorization. So instead of this is like this is the component of my vector xyz, and at the top index, that's the number of position of my vector in my vector field. So instead of taking one vector and putting his three components into the register and doing this kind of operation for each vector, we do blocks where we put when we first operate on the x components of 4 different vectors and do this operation for each of the vector components. If you implement this correctly, then you're not wasting any registers, and your code will scale to further possible bigger, longer architectures like AVX 512 or if GPUs. Of course, like for GPUs, you need to do some more work for the algorithm to work. But like in general, this is what you should be doing. So so you're losing this like natural thinking of putting a vector into a vector. Suddenly you need to decompose the vector into its individual components and work on those. So it needs some code restructuring for this to work. The types, as I said, those are called packed data types, and you have to map your types, your numbers into those packs. So if I have a an array of floats, I need to load it to the register. If I mean, I need to. So on modern compilers, you don't need to do this intermediate step. You can immediately initialize the register with like in the code like this, and then then use the plus operation. So like in with modern compilers in C++, it looks like this. This is a pretty natural syntax. You don't need to think about it too much. And and again, very often the compiler will do this for you automatically, so you don't need to actually handle those registers and special functions by yourself. I'm just like showing that you actually know what is the compiler basically doing behind the scenes. If you, the other option is to use vector instruction extensions of your specific compiler. So, for example, GCC has this attribute. It's a like extension specifically to GCC. And when you create your type as this, then like you were basically type defining it to be an integer with an attribute. So then again, you can use this type kind of the same way as you would be using a four element array with the basic arithmetic operations defined for that type. And yeah, so this is again something you can do by hand, but you don't need to. Maybe like on this level with some high def or something like that. Or if your loops are not too difficult, then have the compiler do the work for you. What you need to think about is how your memory is laid out. This is important because, as you've seen, the memory accesses have different latencies. So from fastest to slowest, fastest is the register. So you would love to have everything in the register all the time. Then you have this fast L1 cache, which is still like small, and L2, L3 cache. Some processors only have one type here. Some have two types with again different speed and or different latency and different size, and then the main memory or like disk and network, which are even slower and slower. Like, of course, some might ask why the L1 cache, which is fast, why it's so small, and why do you there is second level of cache? Why is not everything like why don't we have the one super fast big cache? And the very easy and kind of obvious answer is it's because of money, because those circuits are expensive and large. So if you could theoretically have this L1 cache of like size, I don't know, several megabytes, but then no one could probably afford that processor, let alone to have thousands of them in a cluster. So we have to live with this. And when data is being loaded from the main memory to the cache, it's never being loaded as this single piece of data. It's loaded in so-called cache lines, which have some predefined alignment. One cache line is like on all x86 architectures 64 bytes. And when you're accessing stuff that is in the same cache line, you always find it in the cache if it has been loaded already. But if the data is not found in the cache, then the whole cache line is put out of the cache. A whole new line has to be loaded in there. And that's, again, an expensive operation, so-called cache miss. And that can, again, slow down your program. So what you try to do is to kind of stream the data to the processor in like how it's laid in the cache lines so that it never needs, so that when it kicks the cache line out and loads the next one, it actually ideally utilizes the full cache line before going to the next one. Yeah, those this is this older but still extremely relevant paper. What every programmer should know about memory, from Ulrich Draper, who's one of the developers of the GNU-C library, I think, and like this other paper, what every programmer should know about float point arithmetics, is newer, and so the original idea for this form of name came from Draper, and this paper is long. It's long, but if you're interested in details of like how computer memory operates and how you can, for example, even measure those effects of those different speeds of cache lines, and because like some of those latencies and this stuff is kind of like proprietary data that the manufacturers will not tell you. So if you really want to know the exact numbers, you have to measure them for yourself. And so some examples of how is that done is also you can also find in this paper. Yeah. So you need to think about how your data is laid out in the memory, and there are again so if I'm streaming if I'm saving my data again, if I save my data in this fashion and then try to read them in this fashion, then you can see that I'll probably have some suboptimal access because I'm not using all the points in my cache line, for example. So you need to think about how you lay out your data, and there are like two basic ways. If you have structured data, for example, vectors, how to lay them out in memory. So the most common one would be an array of structures, because my single member is a vector, a structure. So all the members of a single vector are next to each other in memory, which is fine when you want to do operations where you access those three at the same time in the same operation, typically sorting. But then there's this structure of arrays model where you have multiple a single structure that holds multiple arrays. So your structure, one array is all the X components of all the vectors. The second array is the Y components of all the vectors, and the last is the Z components of all the vectors. And this is kind of like vectorization friendly. It's much better suited for horizontal vectorizations because in horizontal vectorization you operate on bunches like this, on bunches of the same component from multiple vectors and at the same time. So this helps you when you want to continuously stream the data in a horizontal vectorization situation. So like I said, very often people look on the structure of arrays as some like holy grail of performance. It's not exactly true, because sometimes, like I said, for example, in case of sorting, this is actually better option. But for many, or maybe even most of the numerical algorithms, this structure of arrays model is better. Of course, the best thing you can do is to have some option to try both, and there are some cool libraries to do that. But of course, if you can do both, then do both, and then test, measure, and profile your program, because like theory is one thing. When you actually go and implement that stuff, you can be surprised by what works and what doesn't. Yeah, there are also options like how to do something in the middle. So if for any reason you need to use this array of structures format, but you would like to optimize your numerical loop somewhere inside, or if you have more pieces of algorithm that perform faster in array of structures and just want to optimize some pieces that work faster in structure of arrays, then you can shuffle the data into those correct registers, perform the operations on those registers, and then put the data back. It doesn't have the optimal cache utilization, but it might be better than if you would be wasting registers on those architectures. But again, like it costs you something to do this operation, so If you want to try it, you should test whether it's actually beneficial or not. And then this another way to do something like a combined idea is this array of structure of arrays. And so you have one large array that contains structures of smaller arrays, where each of the array is typically the size of the uh, vector register. So again, this is like something in the middle, and it also helps you if you often access multiple members of the same vector because they are not that far away in the memory. So they might even like some of them like fit in a single cache line in single precision, and it still has good parallel good streaming access properties for the horizontal vectorization situation. I think this is the last thing about vectorization, and that's alignment. That again can be important in C, C++ code, or even, I don't know, is there one who programs in 4chan? 4chan, yeah. Yeah. So like in those like lower level programming languages, let's say, you might need to think about alignment. Alignment is the position of the beginning of the data structure in with respect to the memory address space, and you have when your program compiles, you will find that there are different instructions for loading aligned or unaligned data into the registers. And those unaligned loading instructions actually perform slower, than take more CPU cycles to execute. And that's one of the reasons. One of the reasons is that the align access is always reading data within boundaries of a single cache line. Unaligned access might cross this cache line boundary, so then you need to load one piece, like you always load full cache line. So you first need to load this cache line and put this part to the register, and then load this, evict this one, load this cache line, and load this part of the register. So that's why it's the main reason why it's slower. And so again, if you use automatic vectorization over compact data structures, that is arrays, or in C++ vectors, or anything that your computer programming language manual says that is a compact data structure, that means that the data is like not interleaved. There are like, it's really, the next number is at the next address. The computer the compiler will emit code that does align access if it's possible, if it deems that it's possible. And of course, the modern compilers are getting better and better in doing that. So now they also able to handle misaligned access. That is, if your data structure is not aligned, it can do this kind of peeled loop. So it first does this non-aligned part at the beginning of the loop separately, then it emits a main loop which does align access, and then the reminder loop which treats the data which was at the end of the big data structure. If he's able to detect that this is the access pattern that's in fact happening. If your structures are explicitly aligned, then it will save the compiler some guesswork, and it might be able to vectorize loops which it otherwise would not vectorize because it wouldn't be sure if he's able to do it. And yes, if you use this array of structures approach to storing your vectors, so you're storing the structures in an array. Then again, in order to use align access, the structure might there might be some padding introduced in the structure that will waste you memory. So as I say, if you have 3 floats but 128-bit alignment, you need to pad this alignment with 32 free bits at each element. So yeah, that gives you an increase of memory consumption and possibly even traversal time for very large arrays. Last thing, what can be vectorized and what cannot be vectorized. Vectorized as in, like you can write a program using vector instructions and, for example, implementing scan for this. But that's not what I'm now talking about when talking about vectorization. When talking about vectorization, I specifically mean, can we do these operations in parallel as they're written here? So it cannot be done here if the operation modifies some previous, if the result of my operation depends on the result of a previous iteration. It cannot be done here when I'm writing to the same variable from more than one iteration, because again, this I cannot guarantee that those iterations will come in the correct order, but in this case, where my result depends on the result of something that's in front of the current the current element I'm operating on. Then in case of vectorization specifically, there's no data race because this read is always performed before this write. So this is a safe loop. So if you have these kind of data dependencies, the compiler should be even able to do this automatically. Of course, there's one thing that the compiler might not realize, and this is an issue of aliasing, because in C and C++, arrays are basically pointers to some to the beginning of the array, and then if you want to access a certain element of that array, what you do is you increment the pointer and just calculate the beginning of the array plus the number of elements, and you go to the position, to that specific position in memory, and like kind of like nothing prevents you to creating like a subarray somewhere in the middle of that array by just like getting the pointer to the middle of that array and having this C array actually pointing into the elements of the A array. And if that happens, it's called aliasing. And if you would then try to vectorize an alias loop, it's like most likely will get incorrect results. And the compiler cannot know that. In like again, compilers are getting smarter and smarter, so sometimes they do know that, they realize that, but in many cases they won't. So but if you know that there's no aliasing in such a loop, you can give the compiler a hint and tell them, hey, this is okay. This is okay to vectorize. There's no aliasing or like some other data dependencies that should prevent you from doing that. And the compiler is free to take that hint into account when deciding whether to auto-vectorize some loop or not. And that's all about vectorization. And now we can try to write some vectorized code. First, we will write some serial code. Then we will use those compiler hints so that it can automatically vectorize some loops of the code. And finally, we'll try to write the same algorithm again, but with explicit vectorizations. So we'll try to create a very simple program. That program will initialize. We will write in C++. Everyone comfortable with C++? Or at least on some basic level. Everyone comfortable with C? Okay. No, it won't be anything too advanced. I mean, regarding the language itself. So we will make a program with where we define an array, or in C++, a compact array is called a vector. So a large array, a large vector of numbers. And we will want to make a square root of those numbers and sum them up. And we'll, so square root sum C, and so in C++, first we need to include some basic libraries. We will use the math, CMath library for the square root operation. Then we will need a vector. That's where we will store our data. Then IOStream is for inputs and outputs, here specifically outputs, so that our program can print something to the terminal. And finally, this is a C++ thing, and let's just put it here from the start. That's the chrono library, which allows us to measure time. So instead of measuring the time from outside of the program, we will have the time measurement here inside the program, and yeah. And so in C++, to save us some keystrokes, we can also use this using namespace std, so that the functions from the standard library, normally you would need to say something like std vector, but if you use this using namespace, then you just can say vector instead. And we can also import namespace std chrono specifically for the time measurement functions. And we write our main function. And first we decide on the size of our problem. Size t is some unsigned, the biggest, it's an unsigned integer which whose biggest value corresponds to the biggest possible value of your virtual memory address mapping. So basically, if you want to make sure that you can possibly that you can express the biggest array that is possible to the size of the biggest array that is possible to address using on your architecture and using compiler. That's what the size t type is for. But it's basically on most architectures is that it's just an unsigned long integer, and we decide how many elements will we hold in our array. Just for making it more readable, I would say, let's say we start with 8 million. Why 8? That's, I'm preparing for like the future parts where we will have vectors of size 8, so that we don't have to like think about this, like what to do with the remainder and stuff like this. So no numpad again. So 8 million, and I will write it like this so that I'm not lost in the zeros. Then let's create this vector of floating point numbers, single precision floats, call it data. Oh, the name of the variable I'm missing here. So vector float data, and we initialize it with an elements, and initialize all elements to be equal to 0.01 f as a single float. Yeah, I think it should be, this shouldn't be necessary, hopefully, in C++. Let's see what the compiler thinks about what I did. And we will also need to store the sum of those floats. So at the beginning, the sum is, of course, equal to 0. Now we start time measurement and write the loop. Then we stop the time measurement and output the result and the time it took to get the result. So in modern C++, the default that should be available for this GCC 13, and I think it's available from C++ 11. The automatic type deduction, so automatic type for variable start, and we get it from this chrono, so-called high resolution block, and we call function now. Here we will later implement our loop, and then auto end again at the end. Okay. Let's do it so that we don't have that much boilerplate. So now I want to know how much time elapsed. So yeah, okay. End time is again high resolution block. Now, it's like sometimes it's better if your code is like more understandable and readable, but I tend to make the code like compact, so I try always like to invent ways how to make it shorter, and sometimes I forget that then I'm at the end the only person who understands what's happening there, and that's also not a good way to program. And now we need to get the duration as a float or a double. It doesn't really matter. Well, it can be slow. I mean, it can be fast, so it can be small numbers here. Elapsed time is of course end minus start, and we print the result. For that, we use C++ streaming operators, which again, a lot of this lives in the STD, in the standard library namespace, which is now imported directly to our main namespace. So cout is the standard output. So this is something that if you run it using PBS, this is what you would find in the O file. You could also use CR, then this would be what you would find in the E file, but this is not an error. So let's print something like sum and the sum and end line and time, then elapsed. This is not a number, it's this special duration type. So we do elapsed.count, and it's in seconds. So S and end line, and it's too long. Yeah, in C, C++, you end the lines with the semicolon, so one command can span multiple lines, and at the end, return 0. Then 0. 0 is is also understood by the Linux command line and most of the other commands as a code for nothing bad happened. Everything went fine. If you would return a non-zero value, then Linux and in general Unix systems interpret that some error happened during the runtime of your program. So this is our basic. This is our basic structure. Okay. I'll try to open it in Vim. I don't know if yeah, okay, those colors are better. So
Jiří, can we restart the PuTTY and change the color scheme? Because
so it's not. Oh no, it's not.
Now it's worse because it's in Vim. It was.
It's even worse. Okay.
Maybe let's restart and just change the color scheme.
Yeah, but I mean, like, yeah. So is this better?
Yes. I mean, yellow on white is not, but it's fine.
So here we need to get the loop in here, and so it will be something like this. The size ti is 0. I n and I and what we do is we add to the total sum the square root of the ith element of the data array. Yeah, looks good.
Oh, so square root of the element.
Yes.
Ah.
Square root of the element. The reason is that it's kind of like a relatively expensive operation, and we want this loop to be more computational heavy than well, like limited by the computational speed and not by the memory speed. So that then we can better see the effect of vectorization.
And like, I finally know, why are we writing plus plus I? I know that there is some difference, but the difference must not affect us in the for loop.
No, it doesn't. It's just that I prefer to do plus plus I because most of plus plus I means first increment I and then read it.
Yes.
So this here it means nothing. But if I did something like A equals
Yeah, I remember
A plus
I plus plus.
I plus plus, then it's actually equals I plus I, and then I equals I plus 1, yeah? Which might not be what you wanted because this looks like, yeah, do like add the incremented I here. Whereas if you write this, then this really is like this, or like actually it's I equals I plus 1, and then
we add the
then yeah, it's just. I mean, really, there's like no in the for loop. It doesn't matter at all.
Yeah, I remember that example from like 3 years ago. We had a C++ in the first year of bachelor experience.
Yeah.
And those like tricky tests from the lecturer when you have like 7 minutes to answer 10 tests. And there are this like all these plus pluses everywhere. You need to calculate it in your hand.
Yeah. Okay. So we save the file, and now again let's do, if you're on the cluster, ideally do it in the interactive environment because we will want this. Maybe not. So okay, let's do it with the default GCC first. So G++ is for compiling C++ programs. Then you need to say the name of the input file, and then with -O you say the name of the output file of the output.
You are on the no. Okay,
Yeah.
because On the login notes, the GCC version is like from 2012. But you can, yeah, I can log in as well. Okay,
yeah. Yeah. So the output, if you don't specify -O and the name, if I just do this, I have a, oh my God, Chrono is not a namespace. Ah, all GCC, okay. So we actually need to get the GCC 13 even for a simple example. Oh my God.
No, you can maybe you can in online for G++ minus std equals C++ 0x, and they
0x is here. Yeah, okay. We will, okay. So now if you didn't put any parameters, the file will be called a.out. So I can run it like this, .a.out. If I want to give it a specific name, then with -O, something like this. Okay, looks good enough. It told me the sum and the time it took to calculate it. Another thing you should be aware of is default optimization levels. There's something that also different between GCC versions. Let's see if it makes any difference here. Oh, okay, good. Oh, of course not, because... Oh, yeah. Okay, no. This is like, wow, it got even slower. Okay, I'll talk about this later maybe, but
Can you show again how did you manage to G++ to work?
yeah, minus
It's minus std, yeah, but it doesn't work for me.
minus std equals C++ 0x.
Oh, I'm not.
Okay.
Why I wasn't writing -03?
O3. This is not a 0, but a big O. This is so -O is an optimization level, but you can see that it maybe even like kind of de-optimized the program. That's this like older G++ version. In the new GCCs, like you usually want to use O3. There are like 4 or like 3 optimization levels and 1 non-optimization. With O0 there's no optimization, and like O1, O2, O3 are like increasing compiler optimization, with O3 being like specifically doing some optimizations that might increase the size of your program, and in some cases actually I mean, not be optimal, but with new GCC, this is not an issue for this example program. But
And don't you get errors
hmm?
don't you get errors in trying to run this program?
No, sure. Well, the lower
No.
So now let's you see that this it completed like really fast, under a lot, under 1 second. So to have some more sensible measurement, we need something that takes some sensible amount of time. So let's increase the size of our problem tenfold, let's say.
You know what's the strangest thing? O1 is even faster.
What?
O1 is even faster.
Okay, that really shouldn't happen.
Like for me, like well, minus big O1.
Yeah, I mean, just ignore this for now because we will later use the GCC 13 that's installed, and yeah, that really works as expected. So let's increase the size to 80 million. Okay, that gives us some this time might be already measurable. Maybe even go to 800 million.
Tam tutaj, tak. Ja teraz nie, to
So, if I put like 800 million elements there, you can see that it only runs for 4 seconds. Maybe 4 seconds is something we can work with. Now, if you look at the results, isn't there anything suspicious about them? Is our program actually doing what it's supposed to do?
Like we have the same number as in 1811.
Yes.
1811. No,
Also, the square root of 0.01 is 0.1. So if I add 80 million times 0.1, the result should be 8 million exactly, right? And even here, this is not true.
We have 2 million. And even before we had like 837,000.
So what happened? Any ideas?
Computational errors have been collected.
That's rounding errors are like one of the typical errors of addition of floating point numbers.
Yeah, because like there will be like something 0,0,0,0,0 and some 3 in the end.
Yes, in the single precision, at some point you arrive to a moment where adding to your number doesn't adding a very small number to your large number doesn't change your number at all.
Yep.
Because the difference cannot be expressed in that precision, because a floating point number is always in the form of a mantissa and exponent.
Yeah.
So if your if your exponent is already something I mean, if the number you're trying to add to your number is lower than, let's say, 1 times 1 over the exponent, then you cannot add it to the you won't see the result of the addition. So if we want to have some program that runs for some measurable amount of time, and at the same time doesn't suffer from this issue, what can we do about it? Any ideas? So the issue here is if you're adding a very small number to a very, very large number. So if we want to avoid this, what we want to do is try to add numbers which are more or less the same size, or like in like within several orders of magnitude, not within hundreds of orders of magnitude. So what we need to do is to introduce some intermediate sum, and let's say we just like do like a local small sum in batches, and then sum the batches. Yeah. So we will also introduce another parameter, batch size. Batch size, let's say we'll do it in batches of 1000, and here we need to modify the loop so that first it goes over the batches, and then it just does the inner calculation for a single batch. So no. Let's call it index, and again we will be comparing this index to the size of the whole array, but we will increase the index in batch size. So I don't need to do like calculations of like how many batches do I need for my array. This will simply stop the iteration when my outer index is bigger than the whole array. Then here we introduce some local or batch sum. And in this inner loop, we only increment the batch sum. And at the end of the outer loop, we add this intermediate local result to the total sum. So sum equals. And then we can, of course, play with the size of the batch to see if to find the correct balance between the batch size and the total size of the array.
I less than batch size.
Yes, of course, you're absolutely right. And it shouldn't start at 0. It should start at index. And yeah.
And you set the batch size to 1000.
Yeah, 1000. Maybe 10,000 would also work. This is something we have to try. I mean, yes, you can theoretically also estimate it from knowledge of the so-called machine epsilon. So machine epsilon is the smallest number that can be added to a floating point number in order so that the change is visible. And you need to multiply this machine epsilon by the by the order of magnitude, by the exponent of the floating point number you actually want to modify. But in this case, it will be, of course, much easier to just try, compile it and see. There, so now that's definitely not a correct result.
I just wanted to ask about this for loop, how we can modify that. So for size the index 0, right? Index from 0 to n minus 1 would go so we have a step of batch size and then
Yes.
we go with batch sum. And just a little from behind, so we have index equals 0, right? And index must be less than n, and we have index plus equal batch size.
Yeah, so I set my index, and in the outer loop, I'm jumping over the index in the batch size in thousands, and then I need to start the inner loop at the actual index of the outer loop and go until index plus batch size. That was the last error I did.
It works, but somehow the result is different. So there should be some other error somewhere because I got new number. Now it's to the power of 7. See?
No, that's okay.
But why? We're going over the same interval. It should be the same sum.
Yeah, but I mean like,
it is a bit faster, yes, but
no.
What's our
This is basically the correct result up to some machine precision. Maybe if I put
the correct is exactly 8 to the power of
to the power of 7. That's the exact result is 8 times 10 to the power of 7. That's the exact result.
okay, I might have missed the beginning then. Why did we at first got only 2 to the power of 6? 2 multiplied by 10 to the power of 6.
That
No,
depends on the number of zeros here.
Okay, sorry.
So yeah, I mean, like if I do 80 here, I think the result will be like exactly correct.
I just skipped some parts of
Still not.
Yeah.
Wait. So with a batch size of 1,000, like I said, it's adding floating point numbers is tricky. Okay, with a batch size of 1,000 and the problem size of 80 million, I actually get the exactly correct number. If I increase the size of my problem while only keeping batch size at 1,000, you see that there's some error introduced, maybe significant one, maybe not. If I do batch size of 10,000 with this 800 million elements, then the error is like less than 0.001%, which might be okay. Yeah.
Yeah, but with 800, it's still some small error.
But yeah, so but the only solution for this algorithm to correctly solve a problem of size 800, you would need to introduce another level of batching.
Right, batch inside of the batch.
Yeah. I mean, this algorithm is absolutely not so critical that you would do that. Yeah, but
it's mainly because it's too close to the type limits, like to the size of the type. So it's like...
yes, yeah. That's exactly the reason. But I mean, like, let's stay at this like single level of batching, because then the result is more or less correct, or like at least somehow approximately, and leave our base program as this, and like consider this the correct algorithm.
So we can just go to 80 million and then set that.
Yeah, 80 million or
800 million.
800 million, or like just put anything divisible by 8 here, so like 400 million will also work.
Which problem are we skipping?
I mean, 80 was a bit too fast, I would say. So I don't know. Like 106. Nah, it's too, because the program will be progressively getting faster and faster, so that we actually see the yeah, okay.
320, batch size 1000.
Yeah, and it takes 1.3 seconds. Okay, that should already tell us something, because like in the end, the program will be more than order of magnitude faster. It will be like 10, maybe 20 times faster. So you still need to be able to see those differences, and also to hide when we will implement threading for this. We also want to be sure that the overhead of using threads is not too large.
Yeah, I've been computing like 800 million and batch size 1000, and I get like 7,099,948.
Yeah, that's
So
fine.
that's like a considerable error.
Okay.
Like how much? I had the screenshot, so here is like 800 million.
With 1000. Yeah. Yes.
And that was like 7.94. So I'm missing like 50,000. Yeah. I need like 2%.
2% is fine. Or maybe it's not. But in your case, change the batch size to 10,000.
Yeah.
And you will get the error under 0.001%. Yes, open. Тут є якісь моменти, де
Gradient accumulation. Ми найбільше збиваємо на менші точки, які окремо обчислюються і додаються до купи.
Це, в принципі, з будь-яким сумуванням великої кількості.
Все, так, зрозуміло. Ми коли зразимо в високі енки, у нас, коли ми беч-сайз збільшуємо. Я не розумію, що з малим беч-сайзом, воно працює гірше.
Тому що ми з малим беч-сайзом додаємо багато.
Знову таки, з іншої сторони. Або ми можемо беч-сайз зробити занадто великим, і тоді воно буде в одну сторону перебільшити, або ми зменшимо його маленьким дуже, і воно буде. Так.
В ідеалі беч-сайз має бути корінь.
Okay, hey, it calculates something. I will look at it later. Let's just like, your result is incorrect, but the algorithm is doing what is kind of like supposed to do on some level. So just now let's try this vectorization, automatic vectorization. And automatic vectorization is actually implemented quite easily. And that is, you include a pragma directive before the loop that you want to vectorize. And which loop we want to vectorize? Of course, the inner loop is the one we want to vectorize here. Yeah. So you can just write, this is a so-called pragma directive, and pragma IV dep tells the compiler that there are no data dependencies and no aliasing in the
it's like automatic vectorization, right?
What?
No, it's not automatic.
No,
it's manual.
No, I mean you name this vectorization as inbuilt or whatever.
Yes, it's this is a hint to automatic vectorizer, to auto vectorizer, that this loop doesn't carry aliasing and data dependencies. Whether it will be vectorized or not is up to the vectorizer. So it might do it vectorized or maybe not. It's like completely up to the compiler. So let's see how GCC 4.8 behaves.
So it's if that, yeah.
Wait. And yeah, here we are. No, we vectorize. With this, I'm trying to disable the vectorizer actually.
It didn't recognize the no.
Because it should be with a single. Nah, well. Or maybe he's actually not vectorizing it with even with the pragma.
What I've read is that it's basically a computation power to vectorize. You can write seamed and it's guaranteed to vectorize.
What?
I've read that if depth is a recommendation to vectorize,
yes,
you can write seemed to guarantee that it vectorizes no matter like
yeah. Let's also try different approach.
Then we are making a square root right?
Yeah, I think this no. This so the problem here is, and the newer GCC can understand it, but is this old one. This line cannot be vectorized.
Why?
Well, because you're adding to you're adding to a single piece of memory you're adding to this is a reduction.
Yeah.
So you would need to use a reduction.
We need to have some kind of an array that is the size of n divided by batch size. And this array
I mean this
values and then we'll add them together.
I wanted to save this idea to the very end. But like another way to have this vectorized using this vector directive is to use a smarter compiler. So in /opt/gcc 13.2, we have a smarter compiler living, but we need to get it to our path together with the libraries that it's providing. So for that, you first need to add this compiler to the binaries of the compiler to your path, like default search path for binaries. So you write export path is the no, and it has to come first. So /gcc also mind that the spaces, like there should be no spaces around this equal sign here, and also no spaces here. Just really write it exactly as I have it. Make sure you don't make an error in this line, because if you do, then you will not be able to run any commands after you hit enter. So this already, if you do GCC minus version, you are at GCC 13.2, but you also need another path. That's the linker path to be exported to your environment, and that's LD library path equals /opt /gcc 13.2 /lib or lib64, and again the previous LD library path.
And important notice, those are underscores, not space bars.
Yeah. So now I will run GCC without this std with O3, because now it will use, I mean, GCC 13 probably uses something like C++ 14 or maybe even C++ 17 as the default C++ standard version. So we don't want this experimental pre-11 version here. And oh, now I'm telling it not to use the vectorizer, so I'm not even sure what the result will be. I didn't try this combination at home.
Better?
Yeah, because this compiler is like really much smarter than the than 4.8. And yeah, okay. So have you exported those paths?
I'm just export path of GCC 13. Okay. Okay, it will break. It's fine.
Unfortunately, because this compiler is, I think, I'm not sure if it's, yeah, I'm not sure if it's not available on the login node or if there were just like some problems. No, on the login node, there are some issues with the glib version. So that's why I needed to use it from the. Yeah, I put it in the Telegram.
For some reason, search still doesn't work for me. So I'm doing it manually.
Ну, за 46 на...
It was created with manual writing.
Hmm. Ah, I meant.
Opt VCC. Так, так, Opt. І тут буде GCC 15.2. Автор GCC 15.2. Просто
So, you know,
The line was not easier commented. Ah, okay, so let's go for it.
Again, you see, I'm really trying hard to force the compiler not to vectorize that thing, and it's again like, yeah, unfortunately, I cannot really do better than this. I haven't found a better way. So I now copy this to some CPP.
Вам не треба, щоб писати, нам треба писати шлях, то який тут описі 17.2 більше. Ну, я не пам'ятаю, треба буде тут культуру, наче це
No.
How does a successful path export look like? Yeah.
One more idea.
So,
I mean, maybe this is really the baseline we will be working with. But again, but maybe it's still struggling with this data dependency that's there. Yeah. Okay, so you see that there's like no difference between the results. Very likely, if you open, I mean, okay, they're not the same size, so they are different, those two files, but very likely both are actually using those vector instructions, and I really didn't find a way to explain to the compiler that he shouldn't do it. On my computer, those two had some differences in runtime, pretty significant, but wait, one more thing. No.
Maybe we can try to look at the pure assembly. What's the difference? Like,
Yes. No. It will be very similar, and I think it's just like for some reason not realizing that it can do the reduction there. So for that,
problem need G++ 13, need 4.8 or 6 or 7. They I just have the old flag, and it constantly says ignoring pragma is dead. But I see some vectorization.
Oh, okay. That's interesting.
But obviously,
Okay. There's another way in modern compilers to implement, like to kind of like force um, the parallelization, and let's see if that works in that weird error case as well. So I just copy my files so that I have it elsewhere as so this one will be using or OMP SIMD. So the OpenMP 4 standard is not just for thread parallelization, but also includes some threading options. And basically, it's just that we replace this if depth pragma with wait. I just that I have it correctly. With OMP SIMD pragma. So we're taking the SIMD system from OpenMP 4, and we need to explicitly tell it that there's this reduction happening on one of the variables. So you say reduction, what type of reduction is happening in there, and so what kind of operation. So it's addition operation and the name of the variable that it should treat as a reduction variable, like this. Then I think you actually need to have this as a separate line. I'm not sure, but just so pragma OMP SIMD and the specification of the reduction that's happening here. So this is again a typically map reduce algorithm. Yeah.
Plus colon bash sum.
Yeah.
Okay, and the body of the loop is data I, SQRT data I, and then we add to. Okay.
Yeah.
Yes.
And now also so again I do G++03. And if you're using OpenMP, yeah. So you need to add FOpenMP, but you okay. So this minus FOpenMP tells GCC to also use the and it's even slower. This isn't that surprising to me because I've seen this if-dep being faster than this OpenMP SIMD reduction as well. The surprising thing for me still is that the the part that shouldn't be vectorized is the same speed as this as the one which is vectorized. That shouldn't really happen, but you can. So what I think is that if we open the sources, we will find that this that these two are actually kind of these two are identical and are better vectorized than the OMP variant. The last one, but we will not do it specifically. I will just send you. I will just send you the file, and you can try it for yourself. And that is with like manual vectorization. So this is basically the same program. I just like keep those STD but it's explicitly using the vector instructions. Yeah. So you can just you need to include this intrinsic header. So you can copy the whole file as I provided it, or you can include the intrinsic header here, and then basically replace this loop with those handcrafted instructions. So first, I save the result of a single vector instruction run. So this is 8 floats, and here I jump over 8 elements at once, load the 8 elements into a temporary 8 element vector. So this loads starting from data I 8 elements into the long register, then perform this summation. So this is really yeah, and save it to this temporary vector, and then so this is this vectorized addition, and after I do this, I basically perform the reduction here by adding to the adding to the total sum via this. I copy the temporary vector to this normal regular array and save to the total sum from the array. So I can just like grab this whole piece and probably need to rename the variables because they're different.
Or if you just copy the whole file itself.
Oh, just copy the whole file, yes. I mean, if
I don't know why, for some reason for me, like insert function didn't work when I need to insert the password. But now when I need to insert 32 lines of code, it did work. I'm happy.
Just if I copy the whole file, I need to make sure that the number of elements is the same so that we're really doing the same algorithm. And also the batch size. I don't know if we use
1,000.
Yeah, we used 1,000.
1,000. AVX.
Yep, that's also what I got.
Ну так, я тільки прочитаю.
Oh my. What's this? Security AX.
What did you change?
There was a typo in includes.
Yeah. And I still get some error.
Instead of include, it was clue something.
I don't have that issue from
Yeah.
but there is
Yeah, me too. Let's look again.
Yeah. Okay, here you need to explicitly tell GCC that it also should use the AVX2 instructions with minus AVX2. Like this probably depends on some default config of the.
I write the output in the same file or what is happening?
Damn. Yes. That of course is mistake.
yeah, now it's 4 times
Yes.
Yes.
Oh my God. At least this worked. So
It's like 6 times faster.
yeah,
No,
yeah.
for you?
Yeah. Let me see for myself. I had like 0.9. Now I have 0.1.
Yeah, but you have it
So it's
still
nearly 9
should
times
be like
faster.
1 tenth.
Then open it.
I mean, we are on different now. So.
Which one are you on? No, it's the same or? I think the same.
It's
There seems to
stations
be.
are no,
I get this.
maybe I have less resources.
There's
It's 4 times. It's 4 times because you had 1, now it's
Yeah. Now it's
3, 4 times. Yes.
more it's yeah, it's all.
so the slowest is this OpenMP vectorization. Then there's this ifdep, and the fastest should be the handwritten one. Yeah. So this is more or less the results you should be getting. Again, the only thing I don't understand is why am I just like really unable to force the original program not to be vectorized at all.
But for that, we have the old compiler, and the morale is like.
Oh, well,
Don't use
that's
old
true.
compilers.
That's actually
Because
true.
basically, old
Yeah,
compiler doesn't do
you can
vectorization for some
yeah.
reason.
The old one doesn't do the
It was 1.4 seconds or 4 seconds.
4.8. And it's weird because I have the same GCC on the laptop as well. Okay, no, I have a slightly newer GCC on the laptop, and there I was able to use this no tree vectorize option to force the compiler not to do the vectorization, and then really the serial version was the slowest of them. And I have this. Yeah, and I really didn't do like anything extra special. It's like G++. Hmm. No, I don't know. No idea.
That includes. Can I have this?
We're trying right now to find other ways to make it faster.
Hmm?
You're trying other ways to make it faster. Or...
No, slower actually. But yeah, let's just live with the fact that auto-vectorization is there if it works, and like can be really difficult to actually get rid of it. Of course, for yourself, you could also try how slower would the program be if we used the SSE instructions instead of the longer AVX ones. I can also share the program. I will then share all the implementations after we go through the OpenMP part. So you can try SSE, and let's make a break. And if you have questions, ask me questions.
Yeah. So just make a proper copy. Make a proper copy and it will work. No, you have a mix of everything. I don't know. So now it's
Okay, so first in just that you actually see the effects of the vectorization and or non-vectorization. So first in this, so first here at std, like delete this using namespace std, and std here in front of the vector, in front of the out and in front of the end lines.
do we do that in a new file?
You can do it in a new file. So this is really this is really a very interesting compiler issue. And if you compile this, you'll get a runtime something around 1.4 seconds. Now, if I copy this file into a new one and just add those if dev pragmas. So here I put pragma if dev. Then the same command, let's do some dev.cpp and output file will be strt some dev. Yeah. Right. Yeah, and now it doesn't see now it doesn't see this issue here. So let's try to do data I. So do it on 2 lines. First, I do the square root, and then I do the sum. Yeah. So I don't know why it doesn't realize that it can vectorize the loop in when the namespace is out. That just like that really shouldn't be that way. So there's something that's confusing the compiler. But it's a good thing for us because then like that's a way to force it not to optimize it, and you can see that it's not optimized exactly here. Yeah. So and now finally this is what I wanted to show you. So we have those versions, the serial version. Then we have this optimized with OMP SIMD. Then we have this one optimized with this ifdep. And finally, we have the AVX optimization. So this is from the slowest to the fastest. Yeah.
I had an issue with ifdep, and it solves by GCC ifdep.
Yeah.
When I put pragma GCC ifdep, it compiles without any warnings so that it emit.
Okay.
I'm not sure why. That's only my issue.
Okay. I mean, I don't even know which is the correct way, but I mean, like, even if I run with this,
Yeah.
Hi, he does it actually. Okay, but he didn't do it.
By the way, you are using right now STD semicolon, double semicolon. Right now, your program is using namespace STD or without?
Yes.
Because I'm not using this one.
Okay. That's a good point. Without.
Oh,
And if you use it, then it disappears magically.
yes. I believe it will.
No.
You write it directly there. This STD, STTCL, and STD vector.
What?
Capital.
Capital. Yeah. Mm. Okay, I'll just try if maybe this would already help. If that was an unknown pragma. Okay. No. Still need to have those on two lines. But yeah, it seems that the correct that it's correct to specify it as pragma GCC of that. But okay, so you've seen the differences in speed. You've seen that even if the compiler is pretty smart, it's still unable to beat this handwritten uh, AVX version when we do the. I think it's mostly because of the reduction step actually, but it like in such a simple case, you should be able to write it somehow so that it will be the um, same speed as the AVX version, but let's not delve into that, and let's continue with the theory, and I will not even switch to double monitors now because we had 16 slides about vectorization. I think you'll be happy to hear that I have 4 slides about OpenMP. Because as I said before, if your program is easy to vectorize, that then will be also easy to make it run in a threaded environment. Just you have to make sure now the data dependency issues are different from the vectorized environment. So what's OpenMP? OpenMP is a programming interface for multi-threaded programming. So it's working on a shared memory systems. You remember that from the earlier lessons that shared memory is basically where each of your processing unit can directly access any given piece of memory they ask for. So it's like basically all computers like that where the CPU is hardware connected to the memory somehow. OpenMP uses so-called declarative approach to threading, and you've already seen it in this in some of the vectorization examples. Declarative means that you specify the regions to be parallelized by some putting a declaration before those regions. So you say the region after this declaration should be parallel, and you don't explicitly say how it's gonna be parallelized. Just say parallelize it, and the compiler is supposed to do that for you. And in C, C++, use those pragma directives to do the parallelization. Yes, it's often used in data parallel scenarios. I don't know, I have this sentence here because everything I talk about is often used in data parallel scenarios. And the number of threads, by default, it's usually the number of CPU cores in your computer. So most of the time you don't need to worry about it. But if you want to set it to some different numbers, then you can either specify it using some command in some function in your program, or with the environment variable OMP num threads. Yeah. How an OpenMP program works, again, it's somewhat similar to what you've seen in the OMP SIMD example. OMP SIMD is a new addition, I think, in OMP standard version 4. But like OMP was original OMP didn't do the SIMD instructions, but only parallel threads. So a very basic loop can be already parallelized with either you declare a block that should be somehow run parallel, so a parallel section. So you say pragma OMP parallel, and like everything that's under that pragma in a block will then be somehow distributed among threads. And so whatever is before is still executed by all threads. And then you say pragma OMP4, and this the inside of the for loop will be divided between the threads. So here you can do some like preparation that each of the threads has to do for themselves. And at the end, divide the work. Very often you're only parallelizing a loop without the need for some special setup. So there's a shorthand for that. Pragma OMP parallel 4 will run this for loop in parallel. And there's also syntax for reductions. And so here we are doing a reduction on the variable called sum. That's this one. So this will automatically not just execute this in parallel, but also take care that this variable is not being rewritten by the individual threads, but it's actually being used as a reduction target. And yeah, you can also explicitly declare this variable to be private. I don't think it's actually needed in this example, but there are different ways to treat variables as like private, shared. If a variable is private, then each thread receives a copy of that variable, and it only exists in that single thread, even if we like store in it. And if it's shared, then all the threads can access it even in the parallel region. So yeah, that was data scope, sharing of the variables and scheduling of the threads. I not want to talk about thread scheduling too much, but I already said in one of the previous lessons that that you can have like a fixed number of threads, for example, running and divide your whole domain into this fixed number of threads, and so like if you have 4 threads, then you give a quarter of your domain to each of the threads, or there are some dynamic scheduling options where your domain is divided into many more parts than the number of available threads, and then the OpenMP schedule on itself decides which thread will work on which part of that domain. Yeah, as I said before, if your code is vectorization friendly, it will also be thread friendly. Cache optimization matters this in very similar fashion as it mattered for the vectorization part, again, because there are some caches which are close to individual CPU cores, like on the CPU die. So this is also important here. And aliasing, I already mentioned before. With auto-vectorization, where the compiler sees that that there's some aliasing issue, potential aliasing issue, even if it's not there, like we've seen in that example where I just added those STD namespaces, and suddenly compiler thought that, oh, there might be some issue with the loop. It will not auto-vectorize, or unless, of course, you explicitly tell him, hey, this is not aliased, so you can vectorize it. With OpenMP, there's no such safeguard, so you need to think. You need to, if you tell it thread to do this in a threaded way, it will just do it in a threaded way and won't watch for possible aliasing issues for you. And the dependency issues are kind of similar to the data dependency issues are kind of similar to the vectorization issue. So the same way as you couldn't vectorize this, like trivial vectorize this, you would need a special algorithm to do that. Here and here, like this was easily, like to do it in a vectorized fashion was easy, because you always knew that you were like skipping from the beginning to the end, and that in a single vector, since you're loading the whole thing from the vector register and putting it to the vector instruction, you don't really have a problem with data races here. Here, there are data races possible, because it might happen that part of the loop somewhere in the front will get calculated before some part at the front, because you cannot like make sure which thread executes sooner, which thread executes later, and similar. This is a similar issue. Again, something that, but those two have a potential solution, or like several potential solutions, and I will show one idea, for example. So if you want to write into so let's say, yeah, you have some algorithm that writes to goes over some cells and writes into two neighbors, I minus one and I plus one. So it needs to write to both sides. Yeah, and it looks like this cannot be threaded because it's like actually a combination of those two issues. So what you can do um, is that you can schedule the threads in such a way uh, that they never actually overlap. So if I make, if I, yeah, so I divide my domain into like red parts and black parts, and first do all red parts at the same time. So if one thread is operating on this one and always like writing to the side, like one element to each side, then when it comes to the end, then yes, here I'm writing into this element, but no other thread is reading it, no other thread is writing it, because in the first stage I'm only doing the red parts. So I store the data here, that's fine. And then in the second stage, I do those which I didn't do, those black parts. So here, again, if I come to the end of the domain and I would like be writing to a neighbor that my thread is not working on now, this doesn't belong to my thread, but it also doesn't belong to any other thread at this time step. So in this way, and this can be like kind of infinitely more sophisticated for like different geometries, 3D geometries. You can have multiple steps like this, and but for some types of this right after right and right after dependencies, uh, this can make your code uh, like threadable or parallelized using threads, even if like directly you couldn't do it exactly, because if you don't do this separation of and like steps, then here if those threads were actually running concurrently, then at some point both can want to write to this single element. So one is here and writing from here, the other is here and also wants to write here, and this kind of data race, of course, would lead to wrong result. Yeah, so that's it basically. The rest of the theory you've heard before, so I hope you have some idea of how it works, and now you have some idea of how to implement it. And the implementation kind of seen before, so we'll use this Pragma OMP parallel for to create our first OpenMP program. And again, we'll mhm. we can start from one of the programs we already made. So for example, let's start from the mhm, serial program. That probably makes most sense. So I'll copy this SQRT sum C to OMP. Yeah, OMP sum CPP. Doesn't matter. P. And there are, of course, again, different ways to go to go over implementing this. We can. Okay, my first example actually used two for loops. Yeah, so I'll just like write it here for you to see, but then we will probably just use this single for loop. So OMP parallel for, and here I calculated the square root uh, um, ah, and here in the second one I do the only the reduction, and I want you to show I mean later I will send you a zip file which has like all the different variants, including those which give incorrect results because they don't include the batching. But since we already written this program with the batching idea in, then this is a parallel for doing a reduction on the variable called sum, and with the it's the reduction is of addition type. And you will notice that while in the earlier example, we are parallelizing the inner for loop or vectorizing the inner for loop. Here, what we're actually doing is we are doing the we are parallelizing the outer loop. So now the division of work will not be over the directly over the indices. The division of work will be over the batches. So each of the threads will get certain batches to calculate. And so this G++, again, let's keep this O3 OMP sum CPP OMP sum and F OpenMP. This W all basically gives you all possible warnings. It's actually a good idea to have this on by default, kind of. But yeah, if I know there won't be warnings. This the important part here, F opening MP is what gives you the OpenMP capability. And yeah, this is the result. It's not that much faster, only like 50% faster. So the reduction takes some time, but most importantly, the overhead of creating the threads is kind of large for such a super simple algorithm. So like we would really need to make the inside of the loop into something something more sophisticated, more longer to calculate than just a square root. Yeah, and also like something that the compiler cannot optimize, because the compiler is also allowed to do a lot of optimizations on the floating point operations.
Is the OMP file?
Yep.
That's the. So just a little bit defined OMP file introduction plus some. We deleted the line with data equals. It's not there because we did it previously.
Yeah. So now, of course, I don't need to have this to calculate this loop separately. I can, of course, do it here. It should save me some time also, because I will not like destroy the threads here and recreate them here. So this is something that looks more like what we had there before. I can actually put it directly here, because we already know that in case the compiler will, I mean, yeah, you probably realize that at some point we're gonna also vectorize the inner loop. Yeah, we know that if we explicitly tell the compiler to vectorize it, then maybe we will need to get that modification of putting this into 2 lines again. Let's see if this helped anyhow. You see that I'm still saying that there's this reduction happening on the sum variable. Again, I'm only doing the thread division on the level of batches, and each of the batches still does quite a lot of work here inside. And okay.
It became worse.
Yes, I really wasn't aware that uh, doing it in those separate loops. So why is this so? He's really shouldn't have that many threads. You know, if the reduction is being only done on 4 threads, I don't think it should be that bad, but apparently it is pretty bad. Let's like try if there wasn't yeah, okay. Because now there's also auto vectorizer still in the play. Yes, it should. It's actually better. So here again, this if it's not separated into 2 lines, the auto vectorizer doesn't realize it can vectorize it. So if I separate it into 2 lines, and before that I had it separated into 2 lines, so it was auto vectorized. Now it wasn't. So now I'm getting auto vectorization and the and threading. At least I think that's what I'm getting, because again, with this vectorizer, it's like not exactly obvious. I'll try to explicitly put this vectorization pragma here, but like from the difference of runtime, I would guess that this was already, yes, it was quite likely, almost surely, this was already vectorized. You can, of course, come up with your way of combining this with the batching with the handwritten AVX code. Yeah. Or we can run this, since we're doing OMP. We can also have this inside loop vectorized using this OMP Cindy. Yes, now it's like more or less the same amount of time. And again, I will send this whole program with AVX, so we can give that a try.
Open the code once more.
Yes.
For me, for some reason, deleting using STD and like I've written STDs near vector, near cout, near end line. Now it does me all the errors about auto and like auto start, auto end.
GCC version. Do you have the correct GCC version? Did you?
I'm writing the like just G++ command, and before I was installing like 13.2, the same that you were doing. I don't know.
Yeah, great. I'll just send this file.
No, because if you each login, you have to process
so I do. Okay, I did log out.
Yes. Yes. After login, you need to load, and getting to the node, you need to put GCC in your path again. Yes.
Okay. Run them again.
So here's this combination of OpenMP and handwritten threading, just that you can see what's the speed of that. Yeah. What? This actually says MIX2. I don't know why it didn't. That's it. AVX. So out of those is the fastest. Again, like I'm saying, this specific algorithm, like the overhead of spawning the threads is quite large uh, compared to just doing a square root and addition. Yeah. So it doesn't make sense. Like, I mean, in here, it doesn't make sense to compare the non-threaded version to the threaded version. Yeah. Because it's just not really, uh, yeah.
You just run that OpenMP ABS file batch, yeah?
Mm-hmm. So, mm, just thinking about how to make this thing run a lot longer. Um,
Some kind of
I'll just use a lot of a lot like much bigger. Oh, and this was also much bigger domain. Just ignore the issues with the.
That's
Ah, okay. That was too much. So 8,000 would be good. Still too much. Okay. Can't really go much higher than we already did. Uh, but hopefully I will manage. No. Damn. Okay, so this is too fast. I need to actually show it on something slower, but still multi-threaded. So let's try this OMP sum CPP. And this is like everything too fast. Yeah, okay, yeah. Um, okay, so I'll try to, because what I wanted to do was to run it like so that it runs for several seconds and then open HTOP and show you that I'm actually really running on multiple threads. What we can instead try is OMP num threads. Um, yeah, and it's not gonna help at all. It's actually, yeah.
Can you show OMP sum file
What?
can you show OMP sum file for a second? This is the program itself. OMP sum CPP.
Yeah.
Ah, okay, that was very easy.
So there's this. If you want to know the number of threads, then from a parallel region, and of course I know why I wasn't getting any speed up. Yeah, so from a parallel region, you can call this get num threads. I mean, this will print it many times, but probably doesn't matter too. When we get num threads,
Jest taka szopla. A такі у вас просто до 300 немає все получиться. Ну, у мене були
so now if I set OMP num threads, something like 1 is just like one thread. Yeah. The reason why I don't see any speed up is that I've just requested one CPU on my node. So all the threads are being executed by the same CPU. If I want to change that, I would have to request, like let's say one node and more CPUs. I hope it will work that way. Now, of course, I need to do this. Yeah. And that was on 16 nodes. You can see that some of the prints are interleaved. Again, that was because before they weren't, because I was running on a single core. So OMP num threads equals 1. Yeah. So this is about 4 times longer, again because the reduction doesn't have linear scaling. Yeah. There's one popular command to measure time, runtime of a script. It's called time. So if you run time OMP sum, it will tell you how much CPU time your program got. Yeah. You see that here it's like a lot more than this 0.1. Let's try with single thread. Let's try with those 16 threads. Let's try with the single thread again. So that's, well, what I want to show you is, is it there? Is it there? Is it there? Yeah, again, this would be really much better than on a longer, on a much longer program. So what can we do with that?
No, that is just not there.
I could show it on something.
What was the command that you ran in the OMP AVX batch CPP file? What was the command when you ran the OMP AVX batch CPP when it's implicitly written?
The AVX one?
Yeah, that one was that one.
And what about it?
Hmm?
What about it?
That one that you sent us in Telegram.
Yes.
I just copied it here. I'm trying to run it and it doesn't work. So what? Maybe I'm just.
It doesn't work?
Maybe I'm using the wrong command in G++.
To compile, you need to add this minus MAVX2.
So it's like G++,
plus, whatever the name of the file, OMP avx.cpp.
Output file, whatever it is.
Yeah. MPAVX at OpenMP and MAVX2.
Mm-hmm. Yeah, it did work. Thanks. And it took like 0.03 seconds to run.
Yeah. I mean, this also of course depends on the size of the problem. But here, I mean, you can see this like 8 times difference actually in this case. Not that bad. So if you want this variable OMP num threads to persist between individual commands, you have to export it because otherwise it only affects whatever is like on the rest of the line. Well, I mean, this is the default, so like this. This will now run for this like 1.2 seconds or something, yeah. And my time command will tell me that the complete user time was like 3.4 seconds. Now, if I go back to 16 threads again, so was that 5 seconds or not? Look what this is doing. So one thread the inner thread loop that's coming from the program says 1.2 seconds, and 4 seconds total out of that, 3 seconds in user time. Could have been like that, right? More or less. 3, yeah, 3 seconds, let's say. Now, if I use 16 threads, that wasn't 5 seconds. That wasn't even 3 seconds. So what happened? Why is this? And that's an important thing, and sometimes even professionals make it. Like recently, a commentator who was testing this new implementation of parallel Python and said that it gives absolutely like no benefit, because if you run it with like this time command, it gives you about the same runtime.
Maybe it is like a combined time.
Yes,
Like
this actually measures the so-called CPU time. So if you have 2 threads running for some time, it
thread
will
one
add
plus
the
thread
values from both of the threads. So
Uh-huh.
this is actually what, yeah, this is like time for all threads running in your program added together. The takeaway from this is just don't use time to measure time of parallel programs. Yes, it's wrong. It's not what you or some others might think it is. And yeah, then you can of course like make yourself as an asshole if you write a whole 6-page articles about how this new real parallel implementation of Python makes no sense because it doesn't give you any speed up on your computer, which you measured using time.
It should give you like the opposite. It should look like the sum of the times is worse. Like here we also see, because you like, yeah, it's better, but when you sum all the times, it's not like the task, it was divided exactly like we ran it on 16 and we divided it by 16. It will be each core is performing it for slightly more, so it will end up in longer time.
Yeah. Yeah. And yeah, I mean, like, of course, it doesn't really make sense for a program that just takes like 1.2 seconds. But because there's especially not in this case, it's like there's a lot of overhead. If I will run it over and over again, like the standard error will probably be pretty high. Well, it's not that bad. But again, if you're running your program over and over again, it might still reside in like the instruction, like the cache, like not the CPU cache, but the memory cache, like loaded from the disk. So that also affects the system time, which in turn affects the full time. But yeah, the user time is obviously not close to that, and you can best see it if you compare it with this single threaded version, when you can like actually, yeah, like now these numbers kind of correspond to what you measure with your clock. Yeah, so that was the last two OpenMP. Of course, there's a lot more about, like I mentioned, this like sharing of the variables and other kind of advanced issues. There are, apart from the reductions, there are also those pragmas for some of the other basic parallel algorithms. You of course can find all of that in OpenMP documentation. but this should already give you an idea of how to parallelize a lot of programs, actually. So now let's skip to the last part of the lecture, and that's MPI. So you remember that MPI is a way to do parallelization on distributed system or distributed memory systems. That means systems where an individual processing unit cannot go to another processing unit and directly look into its memory. If it wants to do it, it needs to exchange messages with the other processing unit. So instead of this being like OpenMP was a declarative way of defining the parallelization of your program, with MPI, you need to explicitly send and receive those messages. So you need to explicitly program your parallelization. And the obvious use case, the most common one, is when your problem is so large that it won't fit on a single node, then you use MPI. You could use MPI if, like, in order to solve your fixed size problem faster, but very likely the communication overhead of communicating over a network, if your problem fits in the memory of a single node, then most likely whatever you would gain by separating it and having different nodes calculated, no, okay, depends on okay, if it's like a data intensive thing, like for example some simulation on a grid, etc., then it's probably not worth in that case. Of course, if it's something purely computationally heavy, then like a search in a tree or something like that, then yeah, then this gives you an option to use more computers at the same time, the same way as previously you would use more cores. You need a special compiler to use MPI. For C, C++, it's MPI CC and MPI C++. Those compilers are basically wrappers around your so-called host compiler. So it's usually a wrapper around GCC that adds some library linkages and like some other stuff. The MPI library itself is usually specifically compiled for your cluster by the cluster administrator, because it needs like some special hardware support for the interconnects and stuff like this. But you can on Linux at least, you can install it on your laptop as well. In that case, you can run multiple MPI programs in parallel on your single computer. That's also possible. Then it's just like, and a lot of programs only employ MPI parallelization, and then on a multi-core CPU, what you do is you run as many MPI processes as you have CPUs. So you don't use any thread parallelization at all. You have a 16-core CPU, so you run 16 MPI processes on the single node. Yeah, it's of course better if most of the time it's better if the if you only run like one MPI process on the node with 16 threads, but that also means that the programmer has to again write both types of parallelization with MPI on the outside and OpenMP on the inside. That is the best way, usually is the best way to do it. Stuff like more difficult on the programmer. When your program is compiled, you run it with, you don't run it directly, you use the MPI exec or the older MPI run command to execute it. And on some clusters which use the Slurm, sorry, on clusters that use the Slurm scheduler, some of them also provide srun, which might be more optimized than MPI exec. Not all of them, but on some of them, it's you usually find this information in the documentation of the cluster. So message passing and program has to be explicitly written so that it sends and receives messages. Kind of means that MPI is in a way the most difficult one to program. So it comes with the largest overhead of all the three ideas we've shown. And the minimal code looks something like this, let's say. Of course, dropped a lot of logic, but first you need to include the MPI library. Even if you're doing C++, you will most likely use the C MPI calls. There used to be MPI C++, there used to be MPI C++ interface, but it has been deprecated about 10 years ago and hasn't been developed for a long time, and it's actually discouraged. People are discouraged to use it, so you should use the C calls directly or find some third-party library. But none of the existing third-party libraries actually implement all the features of MPI. So it will be C code, even if we would be in a C++ program. So you include the header, then you need to do some initialization, and typically you find the so-called rank of that's kind of like an ID of your running process within the pool of all processes, and world size is the size of the pool. So world size gives you the total number of processes, and world and rank gives you the ID of your actually running process in this full pool. Also, I'm saying process really here means that after you compile the program and run it with MPI exec or MPI run, it will run. I don't know. You say to run on 10 nodes or like to run 10 processes. It will really run the exact same program 10 times. So what exactly is that program supposed to do? For example, whether it's like the one who's supposed now to send something or the one who's supposed to be receiving something has to be decided inside the program based on its rank, basically. So you have to explicitly send messages. So you also need to explicitly receive messages. And in both cases, you need to know who are which ID, which rank are you talking to. So if I'm sending, I need to know whom am I sending to. If I'm receiving, I need to know who's supposed to send me a message. And if this is done incorrectly and I'm trying to send message to number 15 and I'm number 1 and number 15 is expecting a message from number 3, which is not sending a message, then your program comes to a deadlock. It just like waits for those messages to be sent and received, and if that never happens, then it's just like waits forever or until the schedule kills it. So like for minimum, you need to know there are also collective operations like send to all. So if one rank sends to everyone, then of course all the other ranks have to wait to receive the message. So, until the message is received, the operation wouldn't finish. And of course, you are sending some data, or you need a place to store the data that you received. So like at the minimum, you have this like partner ID and some place to store the payload. It can be a single number, it can be an array. There are many. The specific type is specified in like you have to explicitly pass it to the sending or the receiving function. And again, you will find all the types listed in MPI documentation. Basically, the most common case is that you're sending a buffer, like an array of values. Then this tells you the start of the array, and the second parameter tells you how many elements you should send or receive. So this is the most common operation that's directly supported by the send and receive operations. So the variable from which to read or where to store, the number of elements to read or store, the type of the elements, the partner, so like the ID of the other side that's waiting for the message, or from whom I'm supposed to receive the message. This one I forgot. Here's 0, so some default. I don't know. I'll have to look it up. This is on which communicator is it communicating? Because potentially you could have some like more communicators. I've honestly never needed it, so I'm not even sure what's a real use case for this parameter. And in the case of receive, there's also some ways to handle some meta messages sent together with the main message. So here, in the easiest case, we just ignore them. So basically, you can like always copy those parts and just focus on this: the payload, the length of the payload, the type, and the receiving or sending partner. And when you're done with your program, when you're finished, you call this MPI finalize function, which closes the network sockets and like just like correctly finalizes the program, waits for all the messages to finish, and returns the control to your main program, which will like this is usually called like at the very end. So it's like expected that after that your program will probably end with like typical like exit command, and that's it. Okay. So let's try to write a simple MPI program. The path variable and like similar path searching variables on Linux have like the paths that you search when you want to write a binary, and like the earlier it comes here, then if it finds it here, then it doesn't continue and gives you that binary. So like here, it first looks into the GCC folder, then the OpenMPI folder, then the slash bin, then the slash user bin, user local bin, user as bin, home. But I mean, like normally I would put this first actually, but so now we should have access to MPICC. Um, usually the yeah, I think we should be fine with does this GCC in the library path, because MPICC should be able to automatically add this link in library path when it's called. So hopefully this will be enough. And again, what we can do as this like simple example would be the square root, but this time the square root sum, but this time over MPI. Now, I'm telling you, this is like a super stupid example, actually. But since we already have written most of that code, it will be kind of like instructive. And then we can actually like finally at the very end write something something interesting. So again, let's start from the serial code we had. So I do CP no, it was called some SQRT sum.cpp and MPI sum.cpp. So there's one thing that's gonna be easier than, for example, in OpenMP, and one that's gonna be, let's say, more difficult. The easier thing will be this inner loop. It can like stay completely the same as it is now. Yeah. The what will be the only thing is that here, okay, with the batching, but yeah, let's divide it over the batches. So each of the processes will get a certain number of batches, and they can just like do this, and in the end, they need to exchange those sums so that some final process with rank 0 will add those sums together, or like will print those sums. So we'll not even be using explicit message sending here. Instead, we'll use read, because the only operation that will be parallel here will be the reduction. Because otherwise we can do everything locally and then just wait for the reduction. So first we need to include MPI.h. And then we need to initialize initialize MPI. Like normally you would put this like argument count and argument value here, but we have none, so I think we can use null pointer here in C++, because this capital null only exists in C. This is like some bit more in C++. Then we want to know how many MPI processes are running. So MPI size. You notice that this is like this C style of instead of actually returning the result by value, it stores the result here in, like stores it into some other value by reference. Please, in C++, when writing your programs, try to avoid this this way of doing it. Like function parameters shouldn't, in general, be used as function outputs. But it's done. It's a common way of doing things because of this C heritage that we have in almost all programming languages. And maybe this even like comes back from Fortran, actually. So word rank tells us what's our ID within this whole group of MPI processes. Now we need to know how many elements should our process be responsible for. So if you know the batch size, then we know the total size. So let's say that the local number of elements will be something like n over batch. So it's like local batches to be more correct. That should be like n over n over batch size over word size. Yeah, it's like the number of elements in one batch. No, number of batches is this. This is number of batches, and this is number of batches divided by the number of workers. So that's that really is the number of the size of the number of batches per worker. Is that true?
And 1,000 batches we divided by workers, but why is there n divided by all of that? Like we have the whole amount of elements in the array. We divided by batch size. We know
the number of batches.
Elements in one batch, and now we all these elements from batch we divide between work.
No. Batch size is the number of elements in batch.
Ah, yes. So we have number of batches then, and divided by batch size, and all of
so that I know how many batches belong to each of the nodes.
We divided by work.
Fraction of batches. Basically, yeah, how many batches per worker?
Yeah.
So we have like whatever 320,000 batches, right?
Yeah.
And we divided by world size, so we know how many batches go to each worker.
Yeah.
Makes sense.
Yeah. So then, how we would use this is that here we know the number of batches. So we start from number of batches per worker times the worker ID. So local batches, the IDs are of course from 0, so times world rank, and we finish at actually local batches times world rank plus 1. Yeah. And again, we increase by batch size.
Isn't it a problem if our world size is not divisible of the total number of
Yes, of course it is.
But we should write rounds.
Yes, exactly. It gets complicated, of course, and it is complicated pretty quickly. Another thing that really wasn't a good idea, actually. So yeah, I can do it like this, and you can see what I'm doing here. But then, like, why to store this huge vector of floats if I'm only using a piece of it, right? So probably we will calculate the number of batches already here. No.
Then we will need what vectors.
Yeah, we probably yeah.
To make it
Okay. Yeah. So no. I'll do it on the vector. So local n. This just gives me the number of data, amount of data that belongs to my my worker, and here the index goes from 0 to local n. And yeah, I'm still increasing by the batch size. So yeah, this probably makes more sense.
No, because if you increase it by the batch size and world size is different, then there is a mismatch.
No. Like this never goes over the batch. This just gives me a starting point. What?
It depends on the world size.
What?
Ah, yes. Okay. Yeah, I understood.
Yeah. So we inside our single program in batches, we calculate this sum, which actually I should. I'll just leave the name sum here just because, like, why not? And also time measurement inside inside MPI programs is like somehow it gets even more difficult when like you have different runtimes on different nodes. So I mean, let's leave it here because we already have it here, but just let's ignore it because it really doesn't tell us that much of important information. So now we have in our process has computed its own part of the sum. So we need to do a reduction on all those individual sums. So we calculate some sort of total sum, and instead of like I said, we won't be using this direct MPI send and receive, especially because we're now doing a reduction, and for there's this MPI reduce, and from what are we reducing? So we're reducing from the local sum, so it's called sum, into the total sum variable just over one element, because this sum variable only has one element. It's a float. Then we need to find the type of the reduction. Again, this would this you would probably find like this. You just Google MPI reduce and see send buffer, receive buffer count, data type, and MPI op. So you would Google again what's an MPI op. And there you find, oh my God. Yeah. So I hope that OpenMPI, there are many implementations of MPI, and OpenMPI is one of them. So let's see how their documentation is. Yes, predefined reduce operations, max, min, sum, that's what we want. Yeah, that's also production, product, logical, and some of the reductions like max and min can also tell you where it found the maximum or the minimum value. So we want to use this MPI sum here. So MPI sum, and then again, if I would look at this MPI reduce syntax, send buffer, receive buffer count, data type, operation, root. So that's the thing I wasn't sure about, and just like we put 0 there, and communicator, that will be a root process. So it can be like, I don't know, started in, so 0, no, 0 and MPI convert, not the main, in our case, only communicator. And at the end, we, okay, I'll remove those timing information. You don't need to remove them, but then, so nothing about this elapsed time anymore. And the sum should be the total sum. Now, if I do it like this, then every process will print this line, because remember, everyone is running the same program. Everyone is doing what's here. So I only want this results or some diagnostic information printed only once by a single process. So this is a very common way where if my rank is 0, so only the first process will actually tell me the result. And of course, at the end of program, I do MPI finalize. Okay. I'll leave it open. Yeah, so like this, you could actually see the whole body of the main function. So everyone got here. Okay, can wait. Okay.
Will it run if you forget to run MPI finalize?
What?
Will it run if you forget to add MPI finalize?
Yeah.
How likely are you to shoot yourself in the foot with that? Like, is it like with closing the files, closing the thread?
Yeah, kind of. Yeah. And yes. There.
Why do you delete data equals SQRT of data
What?
in one of the for loops in the middle of the screen, right above batch sum plus equals was data equals SQRT of data. And we delete it.
What?
So right above your cursor, there is a batch sum plus equals line. Right below. In the
Batch sum plus equals this one, yeah?
Yes, and there was a data of I equals SQRT of data of Y. Why did we do this?
So why we made one line instead of two lines? Because it was like data equals security data and
this thing that was because of the auto vectorizer. Because the auto vectorizer wasn't able to vectorize this, but it was able to vectorize this. Really, like that's like not really a necessary piece now with the MPI version. Yeah. But yeah, this would be how we did the vectorized versions. So I'll just try if I made any errors. So let's try to compile the thing. MPI some CPP, MPI some. So, well, that's some typo here. Of course, this should be the end sign and not the dollar sign which I had there. Ah, okay. So maybe this will already run. I mean, anyone needs more time to write the program? No? No? No. Okay.
Can you remind the path you need to add for OpenMPI? Can you put it maybe in the chat? I missed that part in the beginning.
So now, if you run it like this directly, it will, okay, it will do something, but like it's not really interesting. What you want to do is to run it with this MPI exec, say how many processes it should have, and yeah. Now, of course, it won't allow me to do it because my resource manager, my scheduler only gave me one process here on this node. And MPI, unlike OpenMP, which will just spawn its threads, even if it has less processors available, MPI will not allow me to do this. So if I ask for 4 processes on the node, now I need to, so I'm running with, this is capital I and this is lowercase l. So now this and the library path.
Have an issue like we're running for 320 million numbers, right? We need to add 0.1 320 million times. We need to receive 32 million, right? In the end, total stuff. Yeah. And I've run the code and it is only 32,000 approximately. Maybe it's just a typo in total sum or whatever, but it's like by the power of 1,000. It must be 32 million and it is only 32,000. So I have displayed and stored only one sum of all the 1,000 batch sums that we were computing.
Mm-hmm. Okay.
And you just run the file itself. So no, yours is all right.
Yeah, then we have some mistake there.
Would you show?
But you run with the exe, yeah? And before you run with the MPI C++. And with MPI C++.
Hmm? That's interesting. But I've asked for 4, not for 2. Ah, maybe it's like dividing by 2. Uh, Yeah, okay. So this processes per node actually allocates the I think it actually allocates the virtual cores and but then the number of slots is half of what was requested because the number of slots is probably given by the real cores. Now anyway, okay, oh, just request 16, and I did one more thing. So I request like 16 cores on my node. One more thing. I will let each process to print its rank. So the out rank world rank size. I just show what it's doing, and then I open that again. So I can do MPI exec. Now I should have, since I put 16 here, I should have 8 nodes available, or like 8 process slots available. No, I first need to MPI C++. Compile the thing. And yes. Okay. So first I request the time. When I get it, I put the correct library path here. Now I compile. And now I can run with MPI exec and 8 MPI sample. And you see that I actually got 8 processes working on that stuff, and this was the total sum. That it really was gathered from all the processes. Let's also put the partial sum here. So local sum. Sum. Okay. Understood. So you see each process calculated its local sum of 4 million, and in the end, those 8 processes gave me 32 million after the reduction. So, I mean, I hope you can believe me that it really was like individual processes doing the calculations. Now, of course, what would be the next logical step is that you do threading inside this MPI application. And maybe because we've seen that in our case, explicit vectorization was also very beneficial. You would do explicit vectorization inside threading inside this MPI application. Okay, the idea was like to have you do it and go drink some coffee, but it's since quite kind of late. I will send you the full program when I find it. So MPI, OpenMP, and explicit AVX2 vectorization. Yeah. Yes. Again, this version with explicit vectorization, yes, we've seen is the fastest one. At the same time, probably hope you will never need to actually write programs like this. It's like usually the compiler should be able to do this for you, and like your handwritten code really shouldn't be faster than what the compiler is doing. I don't know exactly why it's the case here. I think the problem lies in the reduction step, but I'm not sure. Anyway, if you write like normally, let's say if you're not a computer science performance-oriented programmer, but a scientist who's writing his yeah, if you are, then probably should learn a lot of other stuff about these vector instructions too. But if you're a scientist who writes his own software, not because his job is to write super performant HPC software, but his job is to do some other science using high performance software, but you need to write this piece of software yourself, most of the time you should be fine with those like pragma-based, declarative-based SIMD commands, and not it really shouldn't be necessary for you to go the most difficult, even if like yeah, in our case here this was the fastest one, but it's also ugly. I mean, like, it's not that much uglier than the MPI stuff, but for the MPI stuff, basically, you have no other option. Yeah.
Finding the amount of code.
This is what I would say is like a good.
Then that's what we just done with MPI. Then
Yes.
Pragma OMP, that's when OpenMP comes into play.
Yes.
And OpenMP does
OMP SIMD is where the
does threading, right?
No, the threading is here, and this is vectorization.
Parallel for reduction. Parallel, this means threading. And
yes,
SMID is one of those abbreviations that we
exactly.
That's vectorization. Okay.
So this is the inner loop is vectorized. Then the local batching is done in parallel threads, and the whole program is sending messages to the neighbors via this. I mean, the whole program is still on the MPI level, as we only have this reduction step in. I think the other example I prepared, which actually does something a little bit more sensible, but I'm afraid it also only uses reduction. So this other example was calculating pi from using this like Monte Carlo method. Estimation of pi, or doing Monte Carlo integration. You generate a bunch of random points and you want to integrate some over some value, a function over some in some region. So you generate a bunch of random points, and at each point you ask, oh, did that point fall in the region or not? If not, you count 0. If yes, you count the value of the function. And if you do this for a lot of points and they calculate a correct average of over the number of points, then you get the estimate of the integral of like, yeah, it's a very crude method, but efficient in some cases where like there are, especially for some extremely difficult functions that you want to integrate, where like basically there's no other option than to use Monte Carlo. Yeah, but like the basic principle, I mean, I went to like a full semester Monte Carlo classes, but yeah, the basic principle came basically explained in two minutes. No, there's of course a lot more, but this is like a very typical introduction to Monte Carlo program. You say how many points to generate, and then you will throw these points into a box sized one by one, and you will count how many of those points fall within a quarter cycle of radius 1.
Mm-hmm.
So that's that's pi over 4. 1/4. I'm just doing quarter.
Quarter
In 1 by 1.
Quarter of a circle with radius.
Yeah.
1.
With radius r. So it's a quarter of a cycle, and a full circle is pi r squared. R is 1.
So I'm confusing the area of a circle, right? With the area of a sphere.
No, in a circle, in 2D, in 2D. 2-dimensional.
I simply forgot this.
So what I need to know is like the maximum possible value of my random number generator, was like somehow this call is actually generating like a number between 0 and some maximum integer. I convert it to a number between 0 and 1, and then ask whether my value has fallen within this quarter circle of so if x squared plus y squared is smaller than the radius of the circle, smaller than 1, and then my estimate is the number of the points that have fallen inside the circle over the number of the total points times 4, because it was a quarter circle, and I know the full value of pi. And yeah, you'll see that from what was that, from a million points. I have an error on the third decimal square. In general, the average error of the Monte Carlo of such a Monte Carlo integrator is with the square root of the number of points. which like is like really not a good thing. So it like converges extremely slowly. But again, Monte Carlo methods are very often used in problems where no other no fast converging method is possible at all.
Let's make a break now.
I mean, this is basically like the end.
Yeah, but there is still like applications like quantum stress, and there is no. I mean, a big break.
Okay.
Because there is already pizza.
Oh, okay. Yeah, that's yeah.
So now we've seen this serial application of calculating pi, and also the other files that you've sent us, they are MPI OpenMP, right?
Yeah. So this is
threading and MPI on top.
yeah.
And the MPI OMP SMID as like all three things together.
No, but that was no. Here I didn't provide the vectorized version because of the random number generator.
There is nothing to vectorize basically.
Yeah, exactly. No, I mean no. You could like do this in vectorized fashion if your random number generator would be able to give you a full vector.
Like two numbers in this case.
No, like the size of your vector.
Yeah,
I've
just
opened
a sequence of.
Yeah.
I've opened the file MPI OMP SIMD that you've sent us, and I see like the MPI stuff, then that Pragma OMP parallel,
Yes.
and then Pragma OMP SIMD.
Yes, but that's not the pi integration. That
is
that's the first example with the square root.
Oh, that's the first example.
Yeah.
And for pi calculation, the methods which give like quadrillion numbers after the point, do they also rely on Monte Carlo? I thought they used something different.
No, that's completely something
because
different.
it would be impossible. Like you can't.
No.
Whatever.
No, those are like some. I don't even know.
I don't remember. I remember that it was something tricky, but I read about it one time ago, and I was just wondering if it's Monte Carlo or not, because
No.
doesn't make sense in that case. I would guess it should be something semi-iterative. Do you know how people calculate pi with like millions times after the dot, after the decimal? And there are from time to time there are record stage. Yay! Now we calculated it to this like tremendous amount of number.
Maybe it's not named Monte Carlo. Maybe there are some.
No, it's not Monte Carlo. It should be something else.
No, it's not. No, definitely not.
I suspect it should be something like that they should again get from some probability distribution, but to calculate something. But что случилось, что ли?
That's a perfect sense.
Неправильно все. А я не поленился и полез работать, и потерялся в литературе. Оказывается, что концепт такой, что это очень архаичная форма времен где-то. Ну вот можно задать вопрос просто.
Вона неправильно, просто.
Она очень древняя.
Ну, це
просто я тут вспомнил, я тут показывал мемчик коллеге. Вы заговорили о Шекспире. Я показывал коллеге мемчик, и мы заговорили о том, что Шекспир вообще плохая вещь, плохая штука, чтобы учить
пример на современной версии. Да. И вот происходит такой прикол, что я вот вспомнил архаику, что в школе меня еще учили, по сути, по переведенным советским учебникам, и там вопрос, если у тебя кто-то формулировался не do you have something, а have you something. И это потом, когда это употреблял, однажды уже закрыться, спросить, что это ты говоришь так сразу, где ты учи? Оно в голове просто сложилось.
Ну да.
А потом я полез в код, и это очень
Simplest one is arctangents, hyperbolic arctangents. More tricky ones, they get into like some elliptic circles, something like multiplication. And then there was some like research paper where they provided some super convoluted formula for it. So it's not something like very trivial.
Зачем ладно, зачем вы грузили? Нет,
So I've sent you via Telegram, actually calculates, estimates pi, and it's parallelized. The inner loop goes in it's not vectorized because, like I said, there is this random number generating part which actually takes most of the time, and the random number generator is not vectorized. It's some default C++ random number generator. So like, even if I tried to do a vectorized version just to see what effect would there be, and like there's absolutely no effect. Like this simple adding, and also there's this if condition which basically leads to need to do masking. Or maybe that's one thing I should mention. I will not explain it because I don't really have a good example for that, but since with SIMD you cannot really do branching, because it's single instruction, multiple data. So you cannot do an if condition that would lead to branches which contain different instructions. And you can somehow emulate emulate if conditions with masking conditions, and so a lot of the instructions have also like a masked version of that instruction, and masking basically means masking is like you have another register which contains zeros and ones, and when there's a one, then the instruction is performed on that register and on that register element, on that vector element, and if there is zero, then the instruction is not being performed. So with masking, you can kind of like emulate if conditions, at least by saying, okay, do this operation only in case something is valid. So in case something valid, you set the masking register, and then the subsequent operations only apply to this register which where you had one, so like it was not masked out. Again, I will not explain it in detail. You can definitely, if you look for masking, there's like masking and conditional laws, that all that stuff is somehow relevant to that. This is the idea. Oh, this is actually nicely explained.
Because it's not good at this. Yeah.
So if you use a greater than operator, for example, on a vector, then it will, of course, compare by element, and then you can use this result and use it with like a logical AND with the mask, and based on that, prefer some perform some operation. And yeah, then it really looks like this. So first, if you want to really like do two branches after that operation, you first evaluate one, or like first evaluate the true ones and the false ones just by like selecting this like performing this operation only on those non-masked numbers. Here I suppose yeah, I mean, if you would be interested in how this works, then this coding block looks like a nice source. But let's go back to the MPI example. And now with MPI C++, 03, MPI CPP, output file name by MPI OMP, and it uses OpenMP. So F OpenMP. Turn on the warnings so that I see if there's not some unexpected error, and there seem not to be any unexpected errors. So now I can test it. Tell me some number. So run pretty fast. So increase the number of trials. It already starts. Looks like it even converges to something like pi, more or less. Now this will take kind of a long time. Yeah. Yeah. Okay. So let's trust that it computes. But yeah, 1415 in a PDF. Oh, okay. It's not bad. Now we want to run it in parallel. So if you have the program like ready here, then exit the node, and let's create a job script and so that we can submit this job using a job script. So I already made it. I'll show it to you. Like I'm still not exactly sure how this ppn selector is actually working on the BitP cluster, because as you've noticed, if I request two processes on the node, I'm only given one. If I request 8, I'm only given 4.
You said we got out of the computer node.
Yes.
And how did we do it? Just CD?
Oh, sorry. No. Yeah. Okay. Yeah. You can either use exit, or you can use logout, or you can use Control D.
Okay, then Control D. And then after writing the script, we will log in and we will.
No.
We create the job which makes it through the scheduler. So we write basically the script for the scheduler.
So the important thing, like why we are now not working on the login nodes, but on the compute nodes, was that on the login nodes, this GCC 13 is broken. And without the GCC 13, I couldn't show you some of the OpenMP examples. So that's the reason. That's the reason we are working on the compute node, even if normally, like maybe the compilation. I mean, compilation of a short program normally you would probably do on a login node. Yeah. So now from the login node, if we create a script like this, it tells us, it says that it wants to reserve 4 nodes and 16 cores on each node. And then, I mean, let's see how this selector actually turns out, because like I said, like when working on a single node, this processes per node, which were actually available on my node, were only half of what I requested here. Yeah, so who knows if this really is going to run on 4 nodes, or if it's gonna be something less than 4. Anyway, I should get the names of the nodes that were used for the job here from the hostname command. And yeah, I don't know if any like easy way to see the number of available CPUs. Try one trick. So when you have this, again, don't forget that since our program was compiled with this GCC 13 and you use this specific OpenMPI library, you need those paths to be in your job file. So
basically, the job file will just contain all the commands that we previously have written by hand. That's what it does.
Yes, but without the compilation. Because we already compiled the program, so we will not compile it again. Also, if we put the compilation command in the job file, then it like you would have like 4 nodes compiling the same program and then writing to the file, and that can also lead to some failures.
So the compilation was done previously with that MPI C++ command, yeah?
Yes.
And we've just so now I see. We've compiled the file. We received like the executable that was put in 0.0, and then we run this executable code that was already combined with // and with some parameters and see what will happen. Okay, I just I just understood what we
With MPI C++, you compile the source code and the CPP file, and that gives you the executable. And with MPI exec, you need this is already the executable which I am running and which I previously made with MPI C++. Yeah.
I just understood what we were doing. It means by compiling files and executable precompiled with different parameters. Just
so again, run on a single node only. Estimated pi to some interesting number. Like, I mean, you would need really a lot of Monte Carlo tries to get to like some interesting number, interesting value of pi. Like, I mean, like probably most of you know a better version of pi than this, right? But I'm kind of disappointed that I don't really think this is like really working the way I want it to work.
oh, so that was a base, right? Oh, we need to give some.
Because
Yeah, the float is lost. So go to let's read for pi. We change from 4 to 8.
Все, вам треба це замало? Так, підключається. Вам треба додому зробити.
This
Так, значить, тепер знову писати.
and now we can
Да. І отут ви що робите? Прописуєте шляхи і так. І вже так. Так.
стати ворогом, чи він розв'язався. Тепер якісь результати ми побачили. А, так? О,
Jiří, can you remind me what were the other flags when you were compiling with MPI C++? You need to add flags.
OpenMP, if you have OpenMP.
То називається script wise.
Oh, I mean, I use O3 just to be sure, but okay, I mean, I'm really following the exact instructions on the website, and yeah, I'm still getting just a single node. Maybe what if I completely like disregard this because this is not in the example. How it shouldn't even give me that many MPI processes, I think. So it's what? It's like running and it will finish, or no. Now it will complain that it doesn't have enough resources. Yeah, of course. Now it complains. So the for 8 nodes should have given me like enough resources to run 8 processes.
Can run something like this and then type the nodes and to see the wording of the nodes. Like
Yeah, I know what you mean. Um, um, mm, there's this PBS node file, right? PBS node file. And I'll also try to go to the, okay, so I look here at koristovania clustera. Which one is correct? The ending clusteru?
Which sentence?
Vykoristování klastera. Koristovača. Posuvník. And like I said, like those ending word endings are like somehow similar to Czech ones, but
using cluster, then it would be
koristování klastera.
Clusterom. Koristování clusterom. OM.
Oh, okay.
There are 6 cases. In 7 cases.
7.
yeah.
7 cases.
That's same as in Czech, but the word endings are different. So that's like the cases are the same and the usage is somehow similar, but the endings are different. So that and sometimes like they're like we use some in different cases than you, so it gets confusing.
The genders of the words. Yeah.
Oh yes.
Especially in German. Especially in German.
Yes. But yeah, even like between so I'll try to I'll try to use the short queue. But I mean, there's like no limits on like the. I mean, yeah, the short queue has a higher priority, but that like shouldn't be a problem. And also in the documentation, I mean, the documentation has some typos. Some of those typos are really weird. So it's obvious no one ever tries to like copy paste from it and run it because a lot of it just doesn't work. Like here, for example, they're missing C. Like this literally tells you there's no MR. Like yeah, but here was the example job. Yeah, this is the example job. It's like really should be with nodes equals and the number of nodes. And it's like nothing. But yeah, what I wanted to do was to change the queue to short. And then
Would you stay on that script for a moment?
yep. Oh,
In the script, so come here, look what you're looking for.
Yes.
The exec minus N8 and the name of the file has been
Actually, I wanted to print whatever was in that file. But very likely.
Well, the way you compiled it, because like usually by MPI OMP, and I here have by MPI OpenMP, so don't make the typo.
The minus N8 and then the
the name of the file that you did when you were compiling with MPI C++, you did in the end minus O and the name, use your name for it to work.
the sub command not found. Huh?
What?
Okay, so I ask it for 1, 2, 3, 4, 5, 6, 7, 8. 9. I ask it for 8 nodes, and it just assigns me. I ask it for 8 nodes, and it just assigns me A47 8 times.
Okay.
That's not correct.
How many?
And also, at the same time, since this processes per node is set to 1, then also it in the error it complains that there's not enough slots to satisfy 8 requested slots. That's the I mean I would say this is some error, or maybe some specific configuration beyond the typical one is needed. I don't know. Or like, I mean, I can use select instead of nodes, but I don't think it will change. But like in general, if you set one node,
Але ви зараз знаходитесь на описуванні меті.
А точно, треба вийти з неї.
Так. І тепер запустити. Але тепер у вас цього не буде, тому що ви щось зламали.
Експортувати заново треба.
Походу треба. А, ні, ви не вийшли. Тому що логав. Тепер має працювати.
А чому воно не шукає включати? Як таке
Я не знаю. Так, тепер ви берете і дивитесь але там немає циферки.
so what works is
Це вас питання. Ну, точніше, перетічок, а потім.
single node job can run like this. I hope. Yes. Also, yes. So this is this weird kind of weird thing, but if you ask for one node and 16 processes per node, then it will allow you to run 8 MPI processes correctly. So you can try it with the numbers you see here. I mean, I try if it's really divided by 2, or if maybe it was -1 instead, but yeah, here's the job file.
Вона працювала? Ну, вам треба зараз повторитися, зайти заново в QSAT файл, скомпілювати, ну, експорти, скомпілювати, подивитися, що він працює.
So, no, it really is probably divided by 2. So this configuration works. Yeah. 16 processes per node on a single node, and then you can execute 8 MPI processes. I'll just try to increase this to 4. What will happen? Because that shouldn't be available from a single node anymore. Yeah. Okay. Okay. Hey, this actually allocated four nodes. You see that okay, there's a nice command that will only give you unique lines from a file. So from unique, I see that but like it just compresses the repeating ones. There's also a command called sort, which sorts the line alphabetically. So if I sort this and pipe this into unique, then you see that I was actually given 3 nodes. When I asked for 4 nodes and 16. So I asked for 4 nodes and 16 processes per node. So I should have gotten 64 processes. Instead, what I got was
the select PBS.
I got 64 processes, but I cannot actually use all of them. That's I mean, select and nodes should be. I mean, I don't know what's the.
Somehow select doesn't work.
No, I mean, if I put nodes instead of select, I think it will be completely the same situation. So when this finishes, I think what we'll see is again a line which has 66 lines, a file which has 66 lines. So WC means word count, and -L is actually counting lines in a file. So 186.105. Yes, so I got 60 because 2 lines are the result of the.
I see the nodes with the name like R46 1, R46 0, and I run Q nodes just after your one, and I see that during the last one, and I see that R46 0 was filled by your job. R46 1 was filled too by your job. R47 0 is partially filled by something. I don't know, but I see again.
It may be me.
61 0.
It may be me.
Therefore, maybe
it literally compresses the names into the one.
That part of the 47, so that may be me, because my output file has hostname A47.
And A47.1 is
Ми бачимо, нема опту.
some simplification. Like we want this.
Що таке?
Zero,
Я вручну їх не
and
брав,
the
Просто копіюйте ці шляхи. У мене не було звідки його копіювати, мені було влом, знову логінити телеграм. Там була адреса прописана, пропущена буквально там 3 символи пропущені. Я не дивився дуже, що на шлях. На шлях
Файли спасані. Ну, це там написали, типа, експорт парампарам.
But I mean that why you will post the suffix -1, -0.
Воно після того, як це буде працювати, так?
That is really weird, but I mean, we would really now need to. Okay, let's make that program really difficult. So. Okay. If you want some good, some useful information about the runtime of your program, put one date command before the run and one after.
Тут теж там я не пам'ятаю, де власне, також я не пам'ятаю, там окс, там не якась інша дивиться.
So we established that if I use one node, 16 processes per node, then I should be able to use 8 individual MPI processes. And now the cluster got super slow. Okay. So I want to doesn't like me anymore. Oh my God. What's happening?
Yeah, same. Oh, wow.
Oh, okay. Got here in the end. So let's make this bigger. But then of course I need to recompile. So I need to go to this node from the job file. I can copy the path and the other path, MPI C++ 03 F OpenMP Pi MPI OMP Pi MPI OMP. Oh, I cannot. But what I can do is Yeah, yeah.
Я тоже пишу кількість раннього препару. Тепер я можу 15 пейдж. А тепер я пишу ls. І ось у мене пай точка. А, ні, 115. О, є. Значить, це був так. О, ага. І робить. Ну, тут є більше 16.
Порядок не може бути. Вони вже не перевіряли, я був не нужно. Так що це
Now I will at least see how long the job really took. And I should see some speed up when dividing this kind of work between the different workers. So is it slow for everyone?
Yes.
Yeah. So that was 10 seconds.
Well.
And of course, there's some overflow. So yeah, I mean, like when you start working with real large numbers, then you know, like overflow is when you have an integer, and when you go to the maximum value of the integer and add one, then it actually like does exactly this in binary, and in this so-called binary complement representation, the next number, if you add one to that, is actually the highest or like lowest negative integer. So yeah, and 10 seconds is still not enough to actually test something on a like in this distributed fashion. But apparently it is somehow distributing the work among different nodes or something like that. At least because if I do last thing I would test is, okay, if in this I put 8 nodes here, it should give me 64 MPI processes, hopefully. And probably didn't, because this loop. Yeah. So how many slots are available in this case? Maybe it's just 8 again. So that's like 5 different nodes somehow. Okay, I don't know. And unfortunately, I really don't know what exactly is happening. What exactly is happening here? Like sometimes. There's some. I mean, what we can do is, but then we still don't know exactly what our program is doing. There's this. I mean, like this should at least. What I would really like to do is actually to run this on 8 node, like one MPI process per node with those 16 CPUs available. But whatever oversubscribe is that it ignores the amount of available slots. And just that we now let's look at the last successful run. That was this one. And yes, that took 10 seconds. And this one was successful as well and took 6 seconds. Again, is that really faster, or is it just some overhead on of the network initialization, etc.? Hard to tell actually. For that, we would need now like something that takes at least a minute to run, while it's doing some calculation. But in general, this is the way how you run MPI programs. I mean, this is the way how you write them. And yeah, it's like just make this 10 times longer, something like. It's like literally just make it run for 10 times longer. The result will be nonsense, because now like everything will be just overflowing and like absolutely not working correctly. But I would really like to know what happens. So first, let's try this 1 and 8. 1, 8. Stop. And yeah, it's running. Great. Running. I will change the job file since the original one is running. I can make changes here and submit it again. The new parameters will be entered to the. But again, I don't know if this usage of this oversubscribe parameter is correct. Normally, I would say it's not correct, but in this specific case, it might do what we wanted to do. Like, you know, like those numbers here in the in the request are the numbers I put in the request, and they look pretty normal and correct. But so yeah, this should run for a while, and after that we should see. Should probably run like almost. This is about 6 minutes. Okay. Hey, the long one actually finished. So let's see if it really really correctly finished. So it ran for a minute. I mean, no, the number will be wrong. That we know, because like there's some overflow that I would need to do like properly. Yeah, that's. No. Here, the only important thing is that it's the same result in both the small one and the large one. Yes, approximately. So, and this took a little bit under 1 minute, and this took 2 minutes. So that's already like a significant difference. So yes, if we use this oversubscribe, it apparently still gives us some speed up. So we're not really oversubscribing, as in filling way more resources that are available.
Sorry, I missed the part that you were.
It just allows me to run. It just allows me to run this many processes, even if the computer claims that it doesn't have enough free slots for MPI processes.
It just assigns to as many nodes as it can, or
no, it just assigns this 64.
Even if you have on the 60.
Even if I'm just on like 8 cores.
And what happens then it like runs, but it says that, yeah, I ran it on 8 cores instead of this 64.
No, yes, because before that it wouldn't run at all. It would just say that there is not enough slots available. So I mean, like, yes, you can use that. Apparently, it still leads some speed up, and that yeah, because that claim that if I request like one node with 16 cores and like I only have 8 slots available, it's weird. And what's even more weird is when I request 8 nodes, that I also only have 8 slots available, the same as when I requested one node. Like that's definitely incorrect. But with this oversubscribe, it's possible to get around it. Maybe there's some very specific configuration specifically for this cluster that has to be enabled in the job file. I don't know. And otherwise, this is the end of the workshop.
Right.
So, thank you. I hope you learned something. I hope it was useful for you, even if some of you are already experienced with clusters. Some are experienced programmers. So like I hope there was like at least something for every one of you. I will send you the rest of the materials, the PDF file from today. I will share in the chat, and I will also zip all the examples that we did today so that you have them in the chat and can explore them later. Okay, so thank you all for coming, and I hope to see you again soon on some other workshop or whatever. Party on Crimea would be the best, but for that we probably unfortunately have to wait for a while. Meanwhile, I'll be definitely happy to visit Kiev again.